one thing I forgot to do. Probably many things I forgot to do. Let me just for afterward, bring up a journal plus plus file. We're not going to be needing this for the reading group, but just so I have it ready. Is the YouTube stream going? Sure is. Okay. But yeah. General relativity, I think. Let me just get in the voice chat, I guess. See if anyone's here right now. And so chapter 1 was a very short chapter. It was kind of seemed like introducing, or I don't know, like it just kind of seems like it's just kind of giving you a taste of what relativity is about. Oh, hey, FizzBuzz.
Hello.
How's it going?
Pretty good.
It's good to have you. So yeah, I mean, thanks for being here.
Yeah, great. Sorry, just making sure my audio's set up.
Yeah. Let me know whenever you're
but
good.
yeah, looked good. Read through the first 2 chapters.
Awesome. Looks like the Nux will be here in a minute. Yeah, so for anyone who's here in chat right now, this is FizzBuzz. He streams, I don't know, like when the planets align and you sacrifice three goats in his name, but he streams. Yeah, you're probably already pretty familiar with general relativity, right?
Yes. Yeah.
Okay.
So I'll be here as like moral support. The problems
We'll
look
need
fun as
it.
well.
Yeah. Okay.
Yeah.
Do you have any like oh, Hemlox is here too?
Hi, am I here?
Hey, yeah.
Hey.
All right.
Awesome.
Am I too loud or too quiet? I never know if the audio is going to be good or not.
Sounds good to me.
Yeah, you're good for me.
Nice.
Awesome. Did you have a chance to read through it too?
Yeah, I just finished chapter 2 earlier today.
Awesome.
Yeah.
So yeah, at least the way we were doing last time is we just kind of would talk about any thoughts we had about the actual chapters and then get into the problems. And hey, Perth. So I think for chapter 1, I didn't have too much of a thought. Oh, Slim. Thank you for the raid. I hope your stream was good. We're just now starting on a general relativity reading group. Welcome in, everyone. Hey, Rex. Yeah, I guess I definitely have some thoughts on chapter 2, but does anyone have anything to say about chapter 1? I don't think I do.
Oh, chapter 1, no.
Okay.
It was pretty straightforward, I think.
The one thing I noticed in chapter 1 at the end is that oh, maybe I'm in the wrong section, but at some point I noticed that ergs and dynes were coming up, and I was thinking, okay, man. Yeah.
I noticed that too. This is in Gaussian units. It's going to take some getting used to.
I think they're okay, right? You just have to move the decimal point for those things.
Yeah, it's gonna, instead of kilograms, meters, and seconds, it's gonna be centimeters, grams, and seconds, I think. For this book's like default units. But yeah, it is just moving the decimal.
He has an appendix on units, but I didn't read it yet. It's only a couple pages, but
okay.
Yeah.
Oh, and then the artist rendition of the Lisa satellites. That's always funny to see.
So the triangle
let's
one?
see, figure.
Oh yeah.
Yeah, the triangle one, figure 1.5. It's like, yeah, it was 20 years away, 20 years ago.
Yeah, okay, 'cause yeah, this is like in space, but the thing that we actually used to detect them was here on Earth, right? I don't know that much about it.
Yeah, yeah, and so they're still planning on launching this in 2035 or something.
Oh, okay.
And it'll be sensitive in a different frequency range.
Okay, that's
So
awesome.
it'll serve a different purpose. That's my
Hmm.
understanding.
That's good to know. Okay.
Yeah, something to look forward to in the next 12 years.
Yeah, to be honest, I assumed
Yeah.
it was just like hypothetical, like it looks like a sci-fi thing. But that's cool. That's actually going to be a reality, I guess. We have to be Rex's bedtime story. I hope you like falling asleep to general relativity. Okay. So I guess on chapter 2, um, the thing that oh well
Actually,
actually
I have one
oh yeah come on.
one more thing on chapter 1, the figure 1.1, where they were talking about the
Oh yeah,
yeah, I was trying to understand this, and
I didn't
I mean we
completely
have this
understand this either.
I didn't really either. The distance along the bottom and mass up the side. And well, I guess what I didn't understand is the universe, where they got some little dots on the line talking about the universe at the quantum gravity scale, universe at the end of inflation, present universe. So I understand, you know, I've been led to believe the universe is expanding, in other words, getting bigger, but I didn't know it was getting more massive. So, like, I thought
Oh,
the
it
Big
does seem to be
Bang
saying
was,
that, yeah.
yeah, I thought the Big Bang was supposed to be everything we got now. All the matter was just in a singularity, and but it was the same mass. So, I just wanted to say that. I don't,
Yeah, so
maybe that's not,
it could be let's see. You know, as you go further in time, um you geez, you can see areas there's more time for light to travel to, right? So
right.
I have in my mind, you know, the I'd have to draw this out on a picture, right? But you can
Oh,
imagine like your past light cone is slowly getting bigger and covering more surface area of the t equals 0 Big Bang. So that could be what it's referring to. That there's like there's more total mass in your past light cone.
huh.
Hmm.
I guess I mean this figure doesn't have time as an axis. It's just distance scales and masses. So I wonder maybe it's just the total distance of the universe as we can predict it versus the total mass. But like the things to the left of it aren't previous in time. They're just different things. Um,
Yeah, yeah, I think there's a lot of like hairiness of definitions that you
yeah.
have to.
Venusian
Okay.
Rex is asking, is gravity a force or space curvature? I think we're learning that it's as a curvature. Like things are moving in straight lines, but the space itself is curved by mass. Oops. And then why light cone and not light ball? Maybe that's for you, Fizzbuzz.
It's a four-dimensional thing. It's a
Okay.
cone. There's spheres there.
Okay.
Yeah, so if you take a slice through it, it's a sphere.
Okay.
You
Um,
just picture it in 4 dimensions. It's
yeah,
Yeah. We're just
easily.
gonna have to, we have to put on our 4D thinking caps for this course. Yeah, for
huh.
sure.
I think the cone idea is like it's like two cones that are like point to point, and you're like the you at your present time at present position are at like where they intersect, and one cone is the future, one cone is the past. Am I remembering that right?
Yes, yeah, exactly.
Okay.
and then it's like right at the top, that's a circle. Really, of course, we're trying to do one direction for time and two for space. Really, there's a third dimension, right? And so instead of circles at the top and the bottom of the cones, they would be spheres, but that's like
Oh,
impossible to visualize.
yeah.
Um,
Okay.
and so I hope it communicates well over voice that I'm saying that while smiling and like totally tongue in cheek. That oh yeah, just visualize it. It's easy.
Yeah, yeah.
Yeah.
Um, yeah, so I definitely had to look at this figure for a while before I feel like I even partially understood it.
Yeah.
They made a distinction between the circle dots and the square dots, and I didn't quite understand that one either, but um, I don't know if it's all that
Yeah,
important.
that's weird.
Oh, other illustrative phenomena where gravitation plays little role are shown by squares.
And like, I think the humans are a square, but I feel like gravity affects me all the time.
Well, don't they say gravity doesn't really affect you? It's just like electromagnetic forces mainly,
Oh, I guess it
unless
like
you
keep my body
happen.
together. Yeah, that's true. But it's great to keeping me here on Earth. Sure,
Yeah.
studying. Hey, I can visualize 4D. I feel invincible. Go you, Rex. Okay. I guess anything else on chapter 1 before chapter 2? I
Nope,
guess not.
not
Okay.
for me.
Um, I think for chapter 2, the main part where I got stuck. Oh yeah, I thought the little story with uh Gauss trying to measure a spherical triangle was cool, even if it's not known for sure. I never even thought that an experiment like that would be like, or the idea of an experiment of just going up a mountain and shining lights never really occurred to me as being possible to measure a spherical triangle here, but it makes sense. But it's also crazy that it wasn't even a big enough scale to really matter.
10 to the
Yeah,
minus 15 radians. 10 to the, yeah, the difference was 10 to the minus 15 radians. That's what they said between the measured and the
uh,
between what is that, Euclidean
yeah.
versus spherical?
Mm-hmm.
well, and here I don't think it would be
Oh,
spherical.
that was mentioned in the errata that it's yeah. I need to pull it up to remember how that works, but they made a correction about that. I should have had this open already.
Yeah, they said be careful not to confuse equation 2.4 with equation 2.1.
Yeah. Um, triangle. Okay, so the Gauss's experiment thing was for triangles formed by light rays in the four-dimensional curved spacetime that surrounds Earth, according to general relativity. And so I assume that's distinct from spherical geometry. I guess I'm not completely clear how, but
Yeah.
Oh, so you know what I did? I just mixed it up, didn't I? I just did exactly what this thing's telling us not to do. Okay.
that's what I was imagining the entire time too, though. So
Yeah, because it's if you shine a light, right, that light is just traveling on a geodesic. So it doesn't care about the curvature of the Earth. So it has to measure something else, like something weird going on with space itself. If there was any angular discrepancy.
What's a geodesic? Is that a part of a great circle?
In this case, it would be the path that a laser beam travels. So you just take a laser beam, you shine it to the other observer, waiting for you on a mountain. Um, and like that line that the laser beam traces out, That's the geodesic.
Okay.
So
And here that's important because like the laser beam doesn't care about what's going on with the surface of the Earth, right?
Hmm.
if I instead had a giant marker and drew on the surface of the Earth, pretending that it's smooth between these points, and tried to measure that, that would be different then, rather than shining a light.
Yes. Yeah.
Okay.
Yeah. Exactly. Or like if you could perfectly measure, I mean, because there's all sorts of like weird mountains and stuff, so you'd end up way off track, right? But
Yeah, yeah.
if you could measure like what am I thinking of? Sea level, right? So sea level would be a much smoother surface.
Okay.
And then that would probably have pretty interesting like angular discrepancy.
Okay.
But it would be different. It would probably be much higher in magnitude than 10 to the negative 15.
That's kind of crazy. Huh.
Yeah, it is. I wonder what the it'd be nice to actually perform that experiment. We probably could. Or not perform the experiment, but like calculate it.
Oh, yeah. Hey, Rushback. If you tunnel straight through, it'll be the same as light. Yeah. I guess it's traveling in a straighter line. Or, yeah. Um, yeah, I think the only other thing that I kind of got weirded out by was when they were calculating distances on a sphere. What figure was it? 2.6. This one had a lot going on.
Yeah, I had a little problem with 2.6. I think their A sine theta is in the wrong place.
I had the exact same concern.
Is that what you were saying? Okay, yeah.
Um, I think
I
you
don't know
can
if it really
justify
matters.
that sine of theta plus d theta is about sine theta if you use the
Yeah,
angle addition.
whole angle approximation. I went through and did that too, and it seemed like it was fair enough. But if you just shifted that A sine theta up, right, to the top circle there,
Hmm.
instead of the bottom circle, then
Yeah,
you could
it should
sort
be
of
up
use
there.
yeah, so then instead of using to measure ds, instead of coming down and across the bottom, you can go across the top and then down the side, right? And then I think you'd get the same sum of squares or whatever, or or at least in that case it would work, right? You'd have A sine theta at the top instead of at the
Oh,
bottom there.
interesting. Yeah, maybe that would have been more clear.
But I don't know if it matters because, like you said, if d theta is small, you can just do. I just did sine of theta plus d theta, and expand it out with the sine of a sum formula, and then take the limit as d theta is small or whatever. And I think it works
Yeah.
either way.
Yeah, it definitely feels like there's a lot more math to get there than they really explain. um,
Yeah, but we got the chops.
yeah, apparently, yeah.
We're supposed to have the
Yeah.
chops. We better, yeah.
Okay, I think that's everything I had to say
The
about
thing
chapter
I
two.
found confusing was
Mhm.
measuring like the ratio of the circumference to the radius of a circle. And see, I'm thinking of the radius of that circle as a sine theta, but it's not. You have to use the radius when you have to use the
Yeah.
radius of the circle as like the arc measured down from the North Pole to your actual circle, right?
Hmm.
Which makes sense. It makes sense, but I got confused for a little bit, like how they were working that out.
Yeah, like the idea of measuring the radius along a curved surface was super weird.
Yeah.
Yeah, definitely. I think that so the way that I think about this stuff is uh I mean you're taking a surface inside of R3, right? And then
Mm,
there are different ways you can talk about curved surfaces. You can talk about just the two-dimensional thing, or you can talk about it as a subset of R3. And
yeah.
I remember being really confused about this, of like from the two-dimensional surface, there's an inclusion map, right? That the two-dimensional surface has a map into R3, and then that map into R3, you can steal the metric from R3, basically. And so then when you measure radiuses in the two-dimensional thing, through this like procedure of stealing the metric from R3, it turns out in 2 dimensions the proper way to measure the distance, right, is going to be through integrals, like in what is this, 218, I think, equation 218.
Yeah.
Yeah. Yeah, and he was talking about somewhere, I don't know where, but he was talking about 3 spheres and 2 spheres, and I thought, I don't really know what this means. Oh yes, page 20. At the top of page 20. Or the bottom of page 19. Yeah, some simple 3D geometries can be thought of as curved surfaces in a hypothetical 4D Euclidean space. For example, the 3-dimensional geometry analogous to the 2-dimensional sphere discussed before is the 3-dimensional surface of a sphere in 4 dimensions, a 3-sphere. And then later he was sort of calling things 2 spheres, and I'm like, not sure I understand what this 2-sphere and 3-sphere is. I'm thinking a 2-sphere. Yeah, I have a chance to make mistakes here, I think. I understand what you're saying. Like the surface of a sphere, right? It makes sense that it's a 2-dimensional object because it can be defined in terms of 2 variables, right? I only need 2 angles
Yeah,
to locate my position on that surface. But yeah, so it's inherently 2-dimensional. But to draw a picture of a spherical shell, I need to draw it in 3 dimensions. Don't I? Maybe not.
yeah, or you could have a map with
Yeah,
a
like
weird metric on it.
a Mercator projection or something, right? Because he was talking about those later.
Yep, yeah, that's exactly right. And the it is weird to call it a 2-sphere, right? Because it's when I think of 3-sphere, right, it's easy to get that confused with the sphere in 3 dimensions, which is not
Right.
what it means, right? It means a 3-sphere is a thing in 4 dimensions
Okay.
with a 3-dimensional surface. The 2-sphere is the 2-dimensional surface, which naturally you visualize in 3 dimensions. So there's like a n-1 issue there that always confuses me.
Okay.
Yeah, I don't think I thought about that one that critically. I just kind of took away what Visbas said, where like we kind of add one, if 3D space is curved, you can think of it as a surface in 4D, or like, you always add or subtract one dimension. Yeah, the actual 3-sphere, they're saying it's a 3-dimensional sphere, 3-dimensional surface in 4 dimensions. Okay.
And I looked at equation 2.6 for a while to see if I could work out how they came up with it, but I gave up. I thought, no, I don't know how they did that. But they said they're going to talk about it in chapter 7, so that's fine. Gonna wait till then.
I think I thought about that for like a
Yeah,
minute and then I gave up. Sorry, what, Visbas?
no, so what is it saying here in 2.6? I read this, but I apparently forgot it.
The volume inside a 2-dimensional sphere of radius r in such a spatial geometry is given by this formula, where A is the characteristic radius of curvature of the 3-sphere geometry.
Oh no. So that's just mean. So this is just being mean.
I mean, it doesn't look that mean, you know, it kind of looks like the kind of stuff we deal with in Calc 2 a lot, right? All these inverse sines and square roots of some or differences of squares and stuff. It seems like I could draw a picture to try and see how they got this, but I couldn't think of what where it was coming from.
Yeah, I'm tempted to like start trying to draw 4-dimensional figures to try to understand what's going on. Right, because you draw this 4-sphere, which looks like a circle, except there are 4 axes on the paper. Oh, whatever. But you'd have to do something. You'd have to understand something like that, at least.
Yeah, it's a volume. You know, I'm happy to stick with distance for now. I'll tackle volumes later once I got a more of a feeling for things.
Yeah, definitely.
But what are they saying this volume even is? The volume inside a two-dimensional sphere of radius r? Like, how's this different from the volume of a sphere that I normally think of?
Well, in 26b, they're saying it's close to what we know, right? For small r over a.
Yeah. And so I guess, is
I
this a
couldn't
sphere
even
that
I couldn't
exists
even
in
see how to.
curved time or in curved space? I think it is
Yeah,
close.
so this is in 3-sphere geometry, I think.
And welcome in, Jamie. Fizbo's put the link there. I also have a posted in my Discord, in the reading group channel. Okay.
Seems like a good book so far.
Yeah.
Yep, agreed.
It does seem like things are going to get like the whole thing they did towards the end with analyzing the peanut geometry. It seems really weird to get used to, but it's kind of like a fun puzzle. Like calculating interesting like ratios of things. Hey, Cook.
I had a little bit of a complaint about this peanut too.
Oh, really?
Yeah, because I graphed that, so 224, right? I put that into Desmos just to see what it looked like. And it looks like it comes into the north and south poles with a slope of 1. So it's kind of a sharp. It has kind of a sharp. I felt like the top and bottom of the peanut should have been sharp, like pointy. But I wasn't sure if that was because I was misunderstanding, you know, misunderstanding something about the dimensions of that we're working in.
Oh, this looks more like a bean. Did I type it in wrong? Sine theta 1 minus 3/4 sine
I
squared.
think you want to make the thetas into x's.
Oh, does this must
I
not
think
look
that's.
like this? Okay.
I'm not sure.
Uh, do I need to put it in polar mode? That's just the grid, though.
Yeah, that looks good. Now just sort of shift it over. You can see your peanut there.
Oh, this is just an outline of the. Oh, okay.
Yeah, now you're sort of going from 0 to. Yeah, there it is.
0 to pi, I
First,
guess.
yep.
And they just like reflect it around. That makes sense. Oh yeah, that slope isn't quite right at the end. Hey, Yanis.
So this says, let's see, reading it carefully,
Hmm.
it says f of theta is a thing that goes in the metric.
Oh,
So f of theta goes in
it's f
2.21,
squared.
Yeah.
and then
It
it's
times
like
a.
you would have to go
Oh.
back to the shape from that metric, from the line element.
So it's not as simple as me just thinking of that being rotated.
Yeah, although it probably does probably is very similar.
Hmm.
But if there's like
Oh.
a square root thing going on there, that would make sense. Is this who I think it is? Dr. Cook?
Oh yeah, that's
Hey,
Cook.
what's up?
Hey.
Hey,
Hey, where are we at?
chapter 2.
Yeah,
Oh,
we're
we
just.
skipped 1, 2, 1.
No, we did one a little bit.
Okay.
Yeah, if
All right,
you have
so
anything to say about it though, please, like we're happy to go back.
No, I just joined in, so I'm still trying to get my bearings. We're talking about a peanut.
We're talking about a peanut.
Yeah.
Oh, yo, what's up? Hey, what's up, Fizzbuzz?
How's it going?
Pretty good. Just doing some grading. It's horrible. So
Oh no, that sucks. That sucks.
it really sucks. This is a good distraction.
Okay. Um. Yeah, that's fair. I guess it's weird that f squared doesn't. It looks even less like a peanut, but I guess we have to consider the formula as a whole, like you said, Fizzbuzz.
Yeah, so I'm. Is there do we have like a shared whiteboard thing up
Oh
yet?
yeah. So
Actually,
it, I,
that's a good point. Sorry, can I say something?
Mhm.
Because they were comparing that equation 224. They were comparing it with where f theta is just sine theta, right? So they said for a sphere, for a perfect sphere, you have f of theta is sine theta. So obviously, I'm wrong in thinking I can just rotate it because that would have a sharp edge too, wouldn't it? Yeah. Okay. All
Yeah,
right.
so
I
there's
take it back. I take it
some
back.
weird mapping, right? It's like x is. I mean, you would do like x is cosine theta, and then sine theta is 1 minus, or square root 1 minus x squared. So there's some weird stuff that turns that like y equals x line into a circle thing.
Okay.
and I have an Excalibur link in the text chat for this voice chat. It's a weird place, but it's kind of like
Awesome.
I don't post the link just like super out there so I don't get trolled with it. If you can't find it, just let me know. I don't need the light cone. Ensure studying. We're just kind of like discussing the content of the chapter, and then once we're done discussing, we'll like work on some actual problems. Starting at theta equals 0, circumference of constant lines. Yeah, the way they analyze it is kind of interesting, where they hold one thing constant and analyze the other variable. I guess it's like visualizing a lot of things in 3 dimensions, though.
Whiteboard put me in as ancient wallaby. That's like weirdly appropriate.
Oh my god! Yeah.
That's hilarious.
So just be your username. And hey, either M Rice or Mr. Ice, welcome in. So yeah, if this was, do you still have something you want to explain on this, or do you feel like it's good?
No, I'm trying to work it out, but I wanted to work it out on a shared whiteboard. So if I have a eureka moment, I don't have to type it all again.
Yeah.
So what are we discussing? Is the question is if you have a general f of theta, what's the corresponding surface?
Yeah.
Yes. Yeah, and 2.21, what does the 3D shape correspond to?
I think the key equation I'm looking at is 222, because that
Okay.
tells you what you can just imagine the circumference of every f of theta. So you can reconstruct the surface by cross section at every
Yeah.
theta.
Mm.
So f of theta equals sine theta is a sphere because at theta equals 0, it's minimal. Then it grows to a maximum at the middle. That's the equator of the
Oh.
Earth, and then south pole. So I think 222 is the way I would visualize this. Given an f of theta, 2 pi a f theta, so it's just a constant scaling, tells you what the circumference is at every constant theta. So it's kind of telling you, I'm thinking of it in terms of cross section, the circumference at every
Oh,
cross section.
Yeah, because my complaint was that the slope of the graph was 1, but so if f of theta is increasing linearly, then the 2 pi, the circumference is increasing linearly, but the area is going to be increasing as a square of that, isn't it? So, like if I
Wait, so
think of it,
yeah, that's a good example. So with f of theta is theta, that
yeah,
means the
That's an
circumference
interesting.
would be increasing linearly with theta. So I would think that would be a cone.
yeah, that sounds right.
Well, so I think here you're right, but so c of theta is this. R or what x of theta is going to be 2.22 divided by 2 pi. So we have a f of theta is one coordinate. The other coordinate would be a cosine
But
theta.
wait, I'm not following. What's x here?
So I'm trying to think about how to get figure 2.27 or figure 2.7.
2.7. Oh, yeah. I mean, I would just draw every theta a circle with circumference 2 pi a f theta. I mean, do you want to turn it into like
Yeah,
a polar
exactly.
graph? Like you want a
Exactly.
function
But
like
then it's
r of theta. You want r of theta phi that traces this out from f. Is that what I'm?
yeah,
Oh, I see what you're saying. Oh, so you want to take a circumference and convert it to. Oh, okay. Yeah, you could do x and
to an
y.
x
Okay,
coordinate. Or like to
I
plot
hear
it in
you.
Desmos, you would do one coordinate at AF theta and the other coordinate a cosine theta. And that would give you a surface parameterized by theta that would trace out this peanut shape.
Okay, so you want x and y as a function. Okay, I hear you.
Yeah, yeah.
I think I
Um,
got you. So there's a factor of cosine that comes in. I think I sort of understand it. I sort of remember when you're revolving something in 3D. I remember reading about this in Calculus 3 at one point. I haven't looked at it for a while.
Yeah, so let's
wait,
see.
okay,
Yeah, that's gotta be.
so Fizzbuzz, y would have nothing to do with theta, right? Or not? I mean, sorry, nothing to do with f, but it would be like just sine theta straight up, or no
But
cosine theta.
yeah, yeah. Like it depends on
Yeah.
which you choose for which. That this would be
Well,
like
I'm trying to do
AF.
the theta equals 0 is the North Pole. So let's say cosine theta would be like the y, nothing to do with f. Am I understanding it correctly?
Yes, yeah, that's a better way to look at it.
Okay, and then x would be um yeah, I think you said it right. The circumference divided by 2 pi, right? Because it'd be f theta because that would be like the radius. Yeah, so I expect the x coordinate would be x of theta would be a cosine theta, and I'm sorry, yeah, I'm sorry, I said that back. Y of theta would be a cosine theta, and x theta would be a f of theta. That's what I would expect.
Yeah, yeah, and then
Do,
that would give us a nice plot on Desmos.
Okay.
do you have that up?
If I knew how to
Okay.
do Desmos.
Oh,
A
I hope
okay.
Don does.
I know what to do with parametric things. I think I just well it was just like
Yeah.
basically a cosine theta and then f of theta.
I
Was that
think
it?
that's right.
Let's see here
No,
the pi
flipped around.
probably.
F theta would be the x coordinate. F theta would be
Okay.
the x coordinate.
Theta
Hey, there we
cosine
go.
theta. Yeah,
Wow.
that's a lot more peanut like.
Yeah, there it is. Yep. Cool.
Nice.
Cool beans, bro.
Cool beans.
Cool
Interesting.
peanuts.
No, like the spherical Lexus.
Cool legumes. Okay. Hey Manon.
Yeah, I mean, going back to
Oh.
the book, I think 222 is the key idea to visualize this.
Hmm.
If you know the circumference of every theta, you can just reconstruct this bit like mentally by cross section.
Yeah, I think it's the way to go. At least that's what it seems like. All right. Anything else on chapter 2? I don't think I did. The stuff with the map projections, I only half understood, but I just wasn't worrying about it that much. Like how you verify some of the preserving, like what properties are preserved.
Hmm.
But yeah, that was kind of just meh for me. Stereographic projection? I don't think so.
So Don Finbuck, did you read this this chapter already? Like
Yeah.
before today?
Yeah, just the first 2 chapters so far.
Okay. How'd it go?
Great. I mean, so far so good.
Yeah, right. It's a beautiful book, right?
Yeah.
Well, I only read chapter 2. Let's hold back our judgment, right? But yeah, so far I like.
Well,
So far I like it.
guys.
So far I like it.
Okay, so Hartlow's glancing at you from across the bar, and you like what you see so far.
That's a good way to put it.
You're
That's a good
you're,
way to
you're
put it.
to approach. Have you already picked problems you want to do, or because I remember at E&M, Don, you used to pick the problems ahead of time, right?
Yeah, so I did call some out. I'm happy to do any of them, but
Which ones stood out to you?
Ivan, hey, welcome in.
Hey, Ivan.
This is one. I 1, 2, 4. I posted them in the Discord, but there's like a list. 1, 2, 4. 5. It was mostly actually. It's easier to say not 3, not 11, and not 12.
Is it in the reading group channel?
Yeah, and there's only 12 problems in total. So.
Oh, I see. Oh, so not 3. That's the only what's missing is 3.
And 11 and 12. But honestly, these all look
Okay.
interesting enough. But one of them needed coding, and I
Okay.
just didn't want to choose all of them.
No,
Do you remember
Mathematica.
do you remember what these symbols mean? Like, what's BSC mean?
B is box.
Like one of the box
which
like
means
figures.
it corresponds to one of the boxes in the chapter.
Okay.
S is
S
straightforward.
means simple, and C
Yeah.
means complicated.
Oh, really?
So I skipped 3 because
Okay.
I had the C, I think.
Oh, you got scared
And then
away.
I think N is programming. I mean, I went down to like try it. I just didn't want to get like stuck on one problem for an entire group.
Oh, okay. That's how it won. What's a right angle corner reflector? What the hell does that mean?
That box talked about like how you can shine a laser at the moon, and we apparently have like those triple reflector things that always point back at you to measure the distance from the Earth to the moon.
Retro reflectors.
Okay.
Like if
this
you
is
have
box
3
2-1.
mirrors
Okay.
at right angles,
Yeah, page 14.
they always reflect light back at you.
Okay.
Yeah, this is a fun fun task that at UCSD they would always task some grad students to work on. It was always they would work on it for a month of like trying to say, well, what happens if you actually shine a laser, right? And so we're not talking about like beam idealization, we're talking about like diffraction and all that. And it would be like you shine like some crazy like megawatt laser and you get back like a few photons from the corner
Oh
of
yeah, they get
Wow.
lost in the scattering. Yeah.
yeah.
Hmm.
So
And there's all sorts of stuff like you have to account for maybe they settled in slightly different ways and the surfaces got a little bit warped, and
Yeah.
ideally it reflects the way that it came.
So
Yeah,
I did have to look up how
Snell's
this
law,
looks.
right?
Yeah.
Storm in chat is saying Snell's law. That's what I was thinking about for this question. I did think about this one a little bit.
And so I brought it into the Excalibur
Well, actually,
too.
do we need
Oh, yeah?
Snell's law? I remember when I took physics in high
No,
school,
I
we
think
did a lot.
Snell's laws
That's for
relative
refraction,
refraction.
right? Yeah, we're not
Yeah,
doing
this is not
refraction. It's just
This is
reflection. So
it's just like the
easier.
angles equal. Like you make a normal line.
Oh, okay. Okay. Now I understand the motivation here. Okay, so I'm a dumb theorist. So my first thought was like, if you want to reflect light, just put like a little flat square of glass, like kind of like what you just drew, Don. But I think the point is that if you're off at all by an angle, that'll scatter, like not back at you. But if you have three planes that come to form half a cube, then you can kind of like mess up a lot and it still come back at you. And so I think A is trying to make you argue that to yourself.
Mhm. Um,
Like between the three walls, it might bounce. Okay, yeah, this is like a geometry problem. I don't know how you would like prove this rigorously for all possible cases.
It says
yeah,
it's
it
a
seems we
right
have to do it
angle
for.
corner. Yeah, so
We can just like
it's
make
like
an
a
arbitrary
billiard
angle
ball on
theta.
a table, isn't it? A billiard ball on a table. It sort of bounces
Oh
off
yeah.
two walls and it comes back parallel to the way it went in.
Yeah, exactly. But okay, but I think there's a three-dimensional aspect to this, right?
Oh, it says to start
Yeah, for
with two
part B.
dimensions, but
Part B,
yeah.
we got to
Yeah,
go
but
3D.
oh, I didn't see B. Okay, my bad. My Cardi B. Okay, I think for B, I think the thing with B is maybe you can argue that like uh the plane of like the incident light ray and the outgoing light ray, sorry, the incident light ray and the reflected light ray will form a plane. And I think any plane will look something like essentially like part A, maybe barring some exceptional cases. That's how I expect B to work.
I
Yeah,
had
I
a
mean, I
nice
think it's just
thought,
gonna be
but
an
I don't.
extension of like part A. Like I don't think they want us to do anything like super crazy. Just kind of extend the reasoning.
Yeah. Yeah, but I think the way that would run is to say that like in part B, there's a plane defined by the incident ray and the reflected ray. That forms a plane. And so you can slice the 3D retroreflector in B with through that plane, and then the picture from A will hold. Will like carry the day essentially. That's what I expect.
Um, and so I guess if this is, I hope this is a somewhat accurate figure to draw here, and I guess the task would be to prove that theta 1 equals theta 2.
Or
Well,
180 plus
no. No, theta 1 plus theta 2 should be 90 in your drawing there.
Uh,
Right?
Maybe, yeah, with the way
Think.
that we've drawn it. I'm trying to justify that. I mean, I guess like we could complete these like normal lines and we have a right triangle, and I guess that would immediately give us what you want, $10.
Yeah, you got a right triangle right at the bottom there, and you can sort of look at
Or yeah.
those. Yeah.
Well, I keep drawing cues. So why does those what if they're equal to 90 degrees, why is that important? Or why does that mean it's going back where it came?
Yeah, we got to use that to prove that the red one and the blue one are parallel. And we got some matrices down below.
Yeah.
Ooh,
That's
okay.
that's what I that's
Oh,
what
like
I
a
was thinking.
reflection.
I was I had a thought about this one. I think this works, right? Couldn't we put our coordinate system, put the IJK at the corner of the cube, and then couldn't we say every time a light ray gets reflected, either the I becomes negative I, or the J becomes negative J, or the K becomes
Yeah.
negative K?
Like that. That's so
Yeah,
much
that's a good
cleaner.
argument. So the key there is choosing the axis to line with the angle or the walls of the mirror. That's nice. Choosing your coordinates to line up with the mirror like that. Yeah, that's sexy.
Yeah, super easy. Disappoints geometers though.
Yeah, I was kind of puzzling over this angle adding to 90 degrees. This is probably obvious, but why is that? I would have thought the condition would be like, well, okay, you need to. I need to stop talking and think.
Hmm.
It's just because the dotted lines have to be normal to the faces of the mirrors, right?
Yeah. And that's what they're doing when I Googled this. Like, they draw that normal line and the angle measured from that is equal on either side.
Well, we could do. I would think we would do something like this, if I can steal
Yeah, go.
your drawing. You know, so this is some like alpha, right? This angle is what is it?
I guess
Pi minus alpha?
pi over 2 minus alpha.
Pi over.
So that's 90 degrees minus alpha, yeah.
Okay. Yeah, yeah, yeah. Let me write this a bit nicer.
And what would these angles, or like, what are they doing for us, I guess?
So can we say alpha plus theta 1 is pi over 2? And then pi over 2 minus alpha plus theta 2 is pi over 2. And right?
Well, I guess one easy goal for the proof might be to extend this line and then prove that this is what this is 2 theta 1 plus alpha, and maybe I could call this beta if we prove that this is equal to 2 to
I want to argue that this angle here is 90.
well, proving that these are equal.
And this one over here is 90. And that should give us theta 1 plus theta 2 is 90, right? Can I say 90 or is it not cool? Should I say pi over 2?
Hey, Papadoria.
Okay, I think I see how to prove this actually. Okay, extend the red and blue upwards and assume they meet at some point far away and call
Oh,
the angle of that point X. Oh,
I need
yeah,
to shift some
sorry,
things around. Yeah,
I
it's
don't
all
have
good.
this Scala open. But so what you'll get is you're assuming that like the red, blue, and green form a triangle where the
Yeah.
top vertex is angle, let's call it X. You can show that X is 0 based on the condition that theta 1 plus theta 2 is pi. So in fact, these never meet. But yeah, imagine extending the red up and the blue up. They assume for the sake of contradiction, let's say, they meet and there's the angle X there at that intersection where there's okay. And then consider the red, blue, green triangle. You have 2 theta 1 plus 2 theta 2 plus x equals pi, 180 degrees in the triangle. And from our condition,
Oh.
theta 1 plus
Yeah,
theta 2 is
yeah.
pi, you get x is 0.
Right. Okay.
So I interpret that to mean that they're in fact parallel.
Yeah.
Nice.
Do you like that, Fizzbuzz?
Yeah, yeah, I do.
Nice. Okay, that's all I'm looking for here is
I
your
think
approval.
X could have been like a chi or maybe a kappa, but X is okay.
Oh yeah, okay, fair enough.
Variable shaming.
Sorry. Wait,
Uh,
it's 2 theta 1 and 2 theta 2.
oh
On the
yeah,
bottom
you're
left
right.
and
Because we
bottom
have
right.
yeah, they're
Yeah.
bisected. That makes more sense. So x equals 0. Okay, I like that. That's the geometric argument. Oh, honestly, the linear algebra argument feels a lot cleaner, but I do like seeing this too. At least for like the argument that Fizzbuzz made with the matrices is, I think it's really easy to extend that to 3D. For the geometry
Oh.
one,
Yeah, yeah, definitely.
Yeah, okay, so I guess yeah, there's my argument where I said for the 3D case, you could always break it down to a plane like this. I guess I wasn't considering the case where there's like 2 reflections before coming back, but that can happen, can it? Like
like it bounces off all three, is what you mean, right?
yeah, like 2 reflections meaning it, or yeah, I guess yeah, sorry, three.
Or
I mean 3. Yeah, it hits every wall, and that can
it's
happen
only
all 3
reflected.
walls.
Yeah. Or yeah, okay, yeah.
Can that happen? That can't happen, can it?
I think so.
Can it happen?
Can I draw this?
Yeah, I think so.
I think so, yeah.
Boom.
I
Boom.
just imagine if you're throwing a rubber ball at the
Yeah,
corner
all
of a
three.
room, right? It can hit the right wall, bounce off the
Okay.
right wall, hit the left wall, come down and hit the floor and come back up.
Okay,
Yeah.
well, I mean, but there's gravity, so my intuition isn't so great there.
Well,
It's
yeah,
not
okay.
purely.
I got to throw it very hard.
Yeah, well, you're stronger than I am, maybe. Yeah, I guess okay. I guess I can see it in my mind's eye. Yeah, okay, fair enough. Okay, yeah, then in that case, I think I like them or the Fizzbuzz's argument. Although, wait, like if you have 2 reflections, you only get 2 minus signs. Like if you only hit 2 of the walls in the 3D case. So
Oh,
is it?
does that make sense? Yeah,
so-
all three should be
so
reversed, right?
Well,
But
there
you
will
only
be
get 2.
special cases, won't there, where it could be coming in like at just the right angle that it's not gonna, like if it comes in parallel to one of the
Walls.
plane, yeah, one of the walls.
Oh,
No, I think the more precise way to say it would be the plane formed by the incident and reflected ray is parallel to one of the walls. And then in that case, it reduces to the picture that Fizzbuzz already drew.
Yeah.
Like you don't need
Okay.
to, you don't need to flip,
one of
you
your
don't need
components
to
would be
flip the
0.
velocity component. You don't need to flip the velocity component perpendicular to that wall. It can remain unchanged, and you still return home. Okay. Yeah.
Yeah.
No, I'm convinced. Okay.
Yeah, I think like you could always choose a coordinate system where like one of the components is 0. And so
Yeah, it would be
it just
0.
needs to be
So
flipped.
-0 is 0.
Yeah.
You flip it or you don't flip it, it doesn't matter, I guess.
Right. Right. Okay. Yeah, that's cute. That wasn't very GR. That wasn't really a GR problem. That was just kind of, that was like a brain teaser.
Yeah, I mean, I was kind of
Yeah.
going with it. I don't know if it'd be all that relevant or not. I guess I'll bring in number 2. I'll do it below here. Why general relativity?
Okay,
not too
I better
specific?
run.
Oh,
I
okay.
gotta keep. I gotta get back to grading as
Keep
much
on the
as I wish I
grind.
could say. Yeah, it really sucks, dude. Pre-med physics, it sucks so bad.
Aw. Well, just the
Good-
one semester,
good luck.
right?
Yeah, just this semester. So,
Oh
all right,
well,
see you guys. It's a lot of
I
fun.
feel your
Thanks for being
pain.
here.
Yeah, it's nice nice talking to you.
Yeah, don't
Yeah,
be a
hopefully.
stranger.
Yeah, so this is the second midterm week. Hopefully next week, and I'll have a bit more time. We can really dig in.
Nice.
Awesome.
All right, thanks,
Right.
guys.
See
Later.
ya.
Yeah.
Okay. So number 2, the center of the sun is much farther away from a terrestrial measurement of angles than the center of the Earth is. Wait, what? It's much further away. As in, like, the sun has a bigger
Yeah.
radius, so it's more spherical geometry? Or, like, the spherical geometry is more pronounced? Is that what they're saying?
Yeah, I guess they just mean the radius of the sun is bigger.
The sun is also more massive.
Well, this is so we're like unfairly getting into space-time curvature here.
So the bigger
Which we
mass
know
curves
because
things.
yeah, exactly.
The bigger mass curve is wants to curve things more, but the flatter relative. I shouldn't use the word relative. If you have so let's see, if we had a triangle of the same area on the surface of the Earth versus the surface of the sun, the triangle on the surface of the Earth would be more curvy, right? The way I would, because it's a smaller radius, so it's a smaller radius of curvature, so more curvature.
I think again it would be misleading to think of these as spherical triangles.
Okay.
So
Yeah.
we really care about like Gauss's measurements, if they did occur, would be like, ideally he'd have carried them out in space, but he couldn't get access to space, so a mountaintop and 2 points on Earth had to do. And then the question is like, for the tides, right? The moon and the sun have similar effects. But is that the case for gravitational curvature? Which is sort of an unfair question because we haven't like got into curvature, right? But we can tell that like something with gravity and geometry has to happen here, because on the left hand side are angles, on the right hand side there's v and masses and stuff. So there's like relativity slipping in here somewhere.
I mean, this is a straightforward question. I'm wondering if it's as straightforward as just I see r cubed on the bottom, but only 1 power of mass on the top. And
I guess it's just m over r cubed then, right? Like which one's bigger, for the Earth
Yep.
or for the
so the radius
sun?
matters a lot more. Like, they're just asking if the radius matters more than the mass, as far as I'm reading it.
Well, it probably depends on the density of your whatever surface you're on, I guess, whatever object your spherical object you're on. I don't know. Is the sun denser? Probably not, right?
I
If the
mean,
sun's made up of
we do have mass per
hydrogen and helium,
volume
you'd think
in
it
this
would be
formula
less dense.
already. I mean,
We got all these numbers in the back inside cover of the book, though.
I think the circle with the plus is Earth, right? And they're
Yes.
just like, circle with the dot is sun, but the formula still applies, just different variables.
Yeah.
But I would think the greater radius of the sun has a bigger impact than the greater mass of the sun. I think is what the type of question, type of answer they're looking for.
Probably, I guess. Yeah. Since it's being cubed.
Yeah.
Yeah, I agree with that. I would interpret this as the measurement is not occurring on the surface of the sun. The measurement is occurring on Earth. And then we're looking at the effects of the sun or the Earth.
Oh, is that what it? Oh, that's what this means. Oh, okay. Okay, I was
but I don't
misunderstanding.
think it would change the conclusion. So
Okay. You know, that
So
makes sense because they did say something when they were talking about Gauss making his measurement. They said they were talking about, you know, calculating the differences based on Earth. But then they said, what did they say? Yeah, together with contributions from the sun and the other planets. So I guess if you really wanted to work it out, you'd have to take everything, all those things into account. But okay, I think I understand what you're saying now. So you're saying we draw a triangle on the Earth, and now we want to compare, for that triangle on the Earth, we want to compare the right-hand side of equation 2.1. Well, no, wait a
are these
second.
the angles that we're measuring? Like the ones inside? Because I'm talking about the centers, and that's
Yeah, if our triangle's on the Earth, then how do we get
it shouldn't
the
matter where
right?
we measure it from if it's on the Earth. Or the terrestrial measurement of angles.
So
I don't know.
so I'm thinking of this as like, okay, so here's a plane, here's, you know, the mountain, here's one of our measurements. Maybe I'll draw it. Whatever. And so in 3 dimensions, this is our triangle that Gauss is measuring. Right? And then we have vectors to the center of the Earth. Which, you know, I'll call this the coordinate. Right? X is the position of the center of the Earth, but then we also have vectors to the center of the sun.
Okay.
And so it's sort of like, that's why my comparison was with the tides. I guess there would be with you know, the sun versus the moon, but it's 2 competing effects on the same red triangle. Did I? It
So
sounds like people are more confused.
No, I understand what you're saying. But I guess I figured that you had to be on the surface of the spherical object where you were drawing the triangle for the right side of equation 2.1 to make sense. That's how I was interpreting it. But maybe that's not true. Like you said, it's relativity, and I don't know relativity yet. So
Yeah, I think that's the difficulty, that it's like we don't fully have the tools to talk about this super precisely yet. But yeah, so the laser beams don't know anything about like the sphere or the surface of the Earth or the radius of the Earth for that matter, right? But they would know if there was some gravitational effect.
okay, so the space where this triangle exists that Gauss may or may not have drawn, it just exists in space, and that space is being curved by both the Earth and by the sun. But it's a hell of a lot closer to the Earth than it is to the sun. So even though the sun is more massive, the Earth is still having a bigger influence on the space where that triangle exists because it's closer. I think
Yes,
that's
yeah,
okay.
100%. 100% is
Okay,
how I look at that.
that makes more sense then.
And I mean, we do technically we do have to run the numbers, right? But it's like,
Just it's the intuition, at least.
yeah. M sun is not like, you know, it's not like 10 to the 60 or something. It's it's like reasonably more massive than the Earth.
10 to the 33 grams.
Okay.
And M Earth is 10 to the 27 grams. Well, those are just orders of magnitude, but
Does I feel like I know this question now, but Fembox, does this make sense to you?
I'm still not, I guess I'm not understanding how we're calculating the radius. I thought the radius was sort of like from your triangle to the mass that's like warping your triangle, right? So I guess that's fine. So, but in that case, we couldn't use radius of the sun, right? We'd have to actually use the distance from the sun to the Earth.
To the triangle.
Yes. Yeah.
Okay, so that'd make that even smaller for the sun.
Yep.
Okay.
Okay. Well, I should type this out quick. um,
Yeah, I was misunderstanding the question. I thought we had to set up two different triangles of the same area, like one hypothetical, one on the Earth and one on the sun, and work out which one would be more kind of distorted. But it does say terrestrial measurement, right? That seems to indicate an Earth triangle.
Yeah.
Yeah.
Okay. So much for straightforward on that question. As long as we interpret it right, it's straightforward.
It does say estimate. It does say estimate. Maybe that's what makes it
Oh,
straightforward.
yeah. I guess so. Okay. The next one I had pulled was number 4, avoiding the complex one, or complicated one.
Let me do. I'm gonna run the numbers on problem 2 just for fun.
Okay.
And I just remembered, Fitzbuzz, you might have to go around the hour mark, or...
Yes, yeah. So I am past time, but
Sorry, please feel free to leave whenever you want. But it's up to you.
yeah, I will hang on here for a few minutes longer.
Okay. Okay, so number 4 says, draw examples of a triangle on the surface of a sphere for which some of the interior angles is just slightly greater than pi. I guess maybe just think about number 4, part A first. Just slightly greater than pi. So like a normal triangle, but slightly greater. I forget who I saw doing this, but I feel like I just saw someone drawing a triangle with 3 right angles on a sphere.
You might be thinking of figure 2.3 from the chapter.
Oh, maybe I'm thinking of the figure. For some reason, I thought I saw it on a stream, but kind of like the easy way to draw it with 3 right angles, which is more than what we want. Is that... Wait, no, yeah, that'd be 3 pi over 2. But you can just like take 2 points on the equator that are, and connect them to the North Pole and make sure they're far enough away that... Oops, I should draw that a little more spherically. Like you can find 2 points on the equator that make a right angle at the North Pole, and as long as you're perpendicular to the equator, you can get right angles there. But this is too much, so I guess we'd want to do a shorter distance along the equator.
Yeah.
I guess it's just slightly greater than pi. It'd have to be pretty narrow.
Yeah, that's a good idea. So you could pull the 2 points on the equator really close together.
Yeah. Right angle, right angle. And then we can just call that like 1 degree or whatever you want.
Yeah.
Okay. And the sum of the angles is equal to 2 pi for part B. Shane, how can a triangle have more than 180 degrees in it? By drawing a triangle on a curved surface. So
You're not allowed to be a flat earther for this chapter.
Yeah.
It just doesn't work.
Or if you are, at least specify what projection you're using. Um, so like if you're just working on a flat sheet of paper, your triangles have to add up, or the angles have to add up to 180. But if you're drawing things on a sphere, it turns out you can make the angles pretty dang big. Might as well be a flat earther. Yeah. Um, and so you have to be on pretty big scales for it to be relevant, but like you can imagine like the route a plane takes with a layover where it connects, three pretty distant points on Earth are potentially ways where like you could get triangles with big angles. It's also possible for space to be curved the other way, like the opposite of spherical, and you can get less than 180, as far as I know. But for like part B here, we have to make it we have to make a triangle that adds to 360 degrees, which is kind of huge. And I think we're gonna do that
can
by
see how to make it just slightly less, or just slightly less than 2 pi.
Well, I think we're gonna be covering, I guess it'd be a quarter of the Earth with our triangle. So if we follow the equator halfway around the entire sphere, and this is where it's getting hard to draw, but we would follow, that's a perpendicular angle, that's a perpendicular angle. We'll follow the edges. I mean, is that really a triangle though? This is a 180 degree angle up here, technically. I guess, yeah, it's a triangle.
Well, wait a second. Does that still count? Is that legit? Does that count as a triangle if the two sides are kind of
Oh, wait,
on
no.
the same side?
No, I don't feel good about this anymore. Maybe we need
I could say that,
do
because I
something
could
else.
say, yeah, check it out. I could say, okay, well, now wait. Can I say this? Can I say, oh, here's another 180 down here? So now I have 540
Okay, yeah.
now in my triangle.
Yeah.
This is actually a hexagon. Okay, so that argument isn't good.
So I would say for this purposes, I think that's a good argument. And maybe you could argue, okay, well it's 179 degrees, and then I mean,
I just slightly change one of the other angles.
yeah, and then
Oh, yeah.
if you wanted to be like really precise about it, you could start talking in terms of like great circles and like actually construct the thing. But that would be, we could do that, but that would be a pain.
Sounds fun to me.
It kind of does, yeah.
That's a right angle. This one is, I guess, nearly a right angle. I'll put like about pi over 2 maybe. And this other one up top is like nearly pi. Not negative pi, nearly pi. So I guess that's how we get around that issue. But I don't do you have an argument for the that looks like a 2? Nice squiggle.
Could we, okay, so the top angle you're saying is about like 179.
Yeah, maybe I should put actual numbers on that to make it, because one needs to be less, one needs to be more. It's not just above or below. So yeah, the top one I guess like 179, and the other one we can make to be 91.
What about thinking about the 2 points where the two points where it hits the equator, right? So you got this point here and this point here. And couldn't you treat the equator like a belt and just let the belt like slide down? Couldn't we take like this?
Like a latitude. Oh, right.
Like,
Still keeping these 2 points on the end the same, or actually sliding, like doing a lower latitude?
I'm saying keep those 2 points on the end the same and just sort of adjust it down like this, maybe.
Oh, that probably works. Yeah.
Yeah. So
I mean,
one
that should work.
one thing that I see as an issue How do I do the cool thing you were doing, Fembox?
Oh, you hit this
Oh, laser
button
pointer?
up here. You hit this button up here.
Oh,
Oh,
cool.
yeah.
So this would have to be 180 degrees apart. So I'm saying that if this is 179 degrees, that the point, the point antipodal from here is not exactly the end of this triangle. It's a little bit off from it.
Oh,
So
yeah.
we would have to account for that in the answer, which is doable, but it's another, slight
And
detail.
Bevo saying, well, wasn't he saying to take the antipodal point? Oh no, otherwise it would be the 180. Okay. Maybe I see
Yeah,
what
yeah.
you're
So
saying now. Okay, yeah.
okay, yeah.
Okay, yeah. We couldn't take the antipodal point, otherwise we run into the 180-degree issue.
Exactly.
Okay.
Yeah, that's what I was trying to do.
But so the way to talk about this, right, is we would have a plane. These great circles, the segments are defined by intersections of the sphere with a plane. So we would have three vectors, right? Alpha 1, and I'm not proposing to actually do this. Yeah, sure, x hat equals 0. We don't have to actually do this. But basically using these three vectors, alpha 1, alpha 2, alpha 3, we could calculate these three angles. And that's how we would actually like construct something to prove beyond a shadow of a doubt we've actually found we found a triangle that has the angles add out to 2 pi.
What is x hat
Can
again?
you tell me what the A alpha 1 x hat is? Is it a dot product or no? That's a scalar,
Yes.
isn't it? Alpha
So
1's
no, I am imagining these to be
Oh,
okay.
vectors. So for example, in in the 90-degree example, or 3 pi over 2 total angle, we would have something like alpha 1 equals something simple like this. 0, 0, 1.
these are measured from the center?
Well, so these are just vectors. This gives us the equation x equals 0, where x hat is x, y, z. So alpha 1 gives us the equation x equals 0. Alpha 2 would give us the equation y equals
Y
0.
equals 0. Yeah.
Mhm. And so these are three different equations
Three
of three different planes.
planes, right? So X is
The
0 is the
sphere.
YZ plane, right?
Exactly, yeah.
Okay.
And the general expression for a great circle it would be easiest
Oh,
to work with in terms of this. That like
I
each
see. So
alpha gives us some circle.
yeah, is alpha just like a normal vector to that great circle plane, kind of?
I think
I'm trying
so,
to think
yeah.
of it like that.
Yeah, I think so. Then that would mean you could make these unit vectors as well. If it's just the normal. Yeah, that makes sense.
so these alpha vectors are the planes that form the boundaries of the triangle that intersect with the sphere?
Yes.
And x hat, why does x hat need to solve all three of them equal to 0? Or what does
So
x
so
hat
it
do?
doesn't. It
Okay.
would solve them separately. So like if this was I guess here I'm thinking of the weird 3 right angle triangle, right? You know,
Okay.
so
Yeah.
like one of these would solve the alpha 1 equation, another would solve the alpha 2.
Or I was thinking you'd even just like do alpha 1 dot alpha 2, and if that equals 0, then you do have a right angle there, and do that for all three of the angles. X, I'm not sure where the X hat, or what the X hat's supposed to do.
No, that would totally,
Okay.
that would work. But then
Okay.
the question, I guess that I'm introducing this notation for is, you know, if we had these slight changes in the angles, right? So we're 1 degree off here, we're 1 degree there. How do we know for sure that
Oh,
we have a triangle that all of the edges are, the word hasn't been introduced, but they're geodesics. They're straight
okay.
lines on the circle.
Okay.
Apparently, chapter 8 is called geodesics.
Okay, well, it's good that
Oh,
we
we have
have to
mean
discuss them in
suspense.
chapter 2.
Okay.
I guess
Here's-
so. Well, just does it kind of make sense why I'm being a little bit of a stickler about this notation here of like,
Yeah.
if we get it slightly wrong,
Yeah.
maybe we end up with something that's not a straight line on a circle.
Yeah, exactly. Because I was thinking of when I was trying to say, you know, take the equator and spin it down. You're exactly right. I was thinking of those two endpoints as being like, you know, poles, right? Endpoints of a diameter of the sphere, and then I could sort of the equator's like a belt, and the fat guy ate too much. He's got to lower his belt. That's what I was thinking.
Yeah.
What about this? Couldn't we? Here's an idea. If we want 2 pi, could we find a triangle where every angle is 120 degrees? That feels constructible, maybe.
Every angle is 120?
Yeah,
Yeah,
well,
I think
Yeah, okay.
100%.
let's just say I have a sphere and I take part of a great circle and I intersect another great circle with that at 120. And then I sort of come down. Now the question is, where do I put? There's going to be some symmetry there that I can exploit to try and find out where do I have to find the 2 points to make the third side.
A little more. My sphere looks a little more like a lemon, but
It's a perfect lemon.
so like you're thinking of like we just start with 2 great circles. We can just call that angle 120, and now the goal is to find whatever third great circle gives us 2 more 120s.
Yeah, so how could we do it?
I may not have drawn the best great circles, but actually I probably didn't. I don't really see it. Well, I guess it would have to go around something like that. Or it might even have to go around on the back of the sphere. But I think I could kind
Yeah,
of
I feel
visualize
like it
it.
might be.
I think it would have to like wrap.
I'm trying to visualize it in my head, but I can't get it in my head.
Freaky Deer Seal, thank you for the follow. Maybe I can draw this a little better.
I mean, the 3 points where this triangle, where the 3 sides intersect, those 3 points, and then the center of the Earth will make some kind of symmetric tetrahedron, right?
Wait, what points will?
I think you're right. The endpoints of the triangle and the center of the Earth.
Yeah. Does that help us find like, so if the radius of the Earth is some constant, can we use that to find lengths of these arcs of these sides. Something like here's the, I got to use a pen. That's the center of the Earth there. And then I want these to be the three.
It's like a curved
Arcs, like,
tetrahedron, I guess.
yeah, and I want these angles here to be 120.
Yeah.
Each one of them. Does that help me find like how far apart those? I want to find the arc length of each of those arcs now, right? You know, that reminds me, they did something in the book on in box 2.2, which I didn't mention on page 17. And I had a little problem with this. They were talking about being able to work out the angle subtended by, what does it say? Imagine that objects of known size p could be identified a known distance d away. Yeah, you got it on the screen now. I'm in the sort of the bottom paragraph there.
Yeah, I see it.
So imagine further that objects of known size p could be identified a known distance d away. If the geometry were flat like a plane, the angle theta subtended by these objects would be p over d. I couldn't quite understand where that came from. So I'm looking at that picture up there of the plane. It's kind of hard to see on the PDF, but there's a plane like tangent to that sphere at the top, and that's where that triangle is inside that plane. So
I think
I didn't know where the distance d was. I didn't know if the distance d was like the two legs of that triangle, or if I was supposed to like bisect it and have a d coming down the middle. But in either way, I couldn't see how I got the angle as p over d really, unless it was a small angle. I was thinking again, maybe that we're supposed to have a small angle.
I think we're observing it from a fixed distance away. One of these distances exists in a flat space, the other one exists in a curved space.
Yeah, and I'm just thinking of the flat one.
Okay.
So I think
Yes,
if I'm
I
reading
think
it,
it is just a small angle thing.
okay.
Because we're like secretly we're thinking we're doing astronomy, right? Well, or we're because we're reading a physics book, and so we're supposed to be thinking about astronomy, where theta is like, some arc seconds or something.
So we're measuring like the diameter of a star that's however many light years away or something. By measuring like how big it looks to us on the Earth or something.
Yeah, I would think that's the idea for this box.
Okay, sorry, I distracted us. It just reminded me of the question we're talking about right now.
I feel like I understood at the time, but now I'm questioning it. But
Great, so now I confused you.
uh, I did think it was hilarious how they provided like the British translation for chips. When they're saying there's a geometry that's like a potato chip, they specify that it's crisps for the UK. I know, I think I get this, but just don't ask me to explain it. So I guess for the 120-degree triangle, we had to figure out some relationship between the kind of vertex of the tetrahedron. Like, I'm thinking, like, wouldn't we need to know something about, like, that angle there? Or, once things get curved, it's...
Or maybe
Well, so-
what are these angles here at this corner?
I guess, yeah, so we
They
can think
should
about
all be-
circumferences.
They should all be the same, but what are they?
So wait, if all the in spherical geometry, if all the angles are the same, is it still equilateral? Or if we're assuming all these angles are the same, I feel
Yeah.
like we're
I would say so.
okay.
Well, if this is a diagram in 3 dimensions, though, right?
Yes. Yeah, I was trying to draw a sort of a circular piece that was cut out of the earth.
Yeah, so that's like the center there of the Earth, or I guess sphere, because the Earth isn't a sphere, but um,
So here, I know I can construct this spherical triangle,
okay.
but I don't know if we want to. But
Oh,
I
is it
can.
too complicated?
Well, it's just. I think it's fine.
Okay.
Okay, so first, I'm gonna take one of my great circles to be along the equator.
Okay.
And let's start X here. This is Z up or is Y up? I guess Z is up, huh?
I
'Cause
like
it's
Z.
X.
Yeah.
Yeah.
Mm.
Um. Okay, so my first great circle is in the XY plane, or I should say great arc. Um, and so that's going to be represented by my alpha vector 0, 0, 1, right? Which represents the equation z equals 0.
Yes, for the XY plane. Yeah.
Okay, and so for the next thing, right, this goes up in some direction. So we have some alpha 2. No idea how we want to parameterize this yet.
So we want to make sure the dot product gives us what we want. Is that where you're going with this?
Yes, yeah, exactly.
Okay.
Right, so first alpha 1, points up in space. Alpha 2,
It's pointing kind of in the X direction, but maybe not entirely.
yeah.
Or we probably orient it so it is.
So I'm thinking, is it as simple as just dot product alpha 1 dot alpha 2? And maybe I'll call this theta 1, which is this angle right here.
I think so, as long as we're all unit
Yeah,
vectors.
if they're unit vectors, right, it seems good.
I think there's a pi minus or something.
Oh.
Yeah, because we do have normal vectors. There's maybe some geometry to work out with what the actual angle between the planes are. Hey, Plasma.
So there's a line of intersection, right? And if we look down the line of intersection, right? So this point is the line of intersection. We have 2 things going off of it. Where one of these is alpha 1. Another of these is alpha 2. Maybe
Ooh.
I should stop myself
It's like
here.
a quadrilateral there. That's why you want pi minus that.
Yeah. Yeah, so what, this is theta 1.
And so what the dot product gives us will be the angle at the top.
Ooh, yeah, yeah. So let me erase this before we get it. Maybe I'll leave some of this.
I think it's just pi minus the inverse cosine. Oh,
Yeah, I think you're right.
because we have two right angles, pi plus theta 1 plus, I guess, inverse cosine. Get to 2 pi. Yeah, okay. So we want alpha 2. Like, that makes it a little bit harder, I guess. Presumably, though, you could find find a theta 1 that does that. And then
Yeah. So it's not too bad, right? Because we want theta 1 to be 120 degrees.
Yeah.
So let's just treat this as a constant, so we don't have to deal with pi over 2 pi over 3 everywhere. But okay, well, alpha 1 dot alpha 2 is just
1/2, I
alpha
guess.
2 z. So alpha 2 z is equal to cos pi minus theta 1. Which is just, am I tripping, or is this square root 3 over 3?
I want to say that's 1/2.
1/2 might be.
root 3 over 3 is
Oh,
oh no,
oh, it's negative. Wait, isn't this negative? Cosine of pi minus all students. Oh no, pi
so
minus.
how
No,
we've
no, no.
defined
We're
it,
good. It's positive. Positive. I think it is 1/2.
uh,
Sine of
yeah,
30 is a
but
half. Cosine of 60 is a half.
theta 1 is 120 degrees for what we want.
Yeah.
But so pi minus that is 60. Okay, yeah. So that's 1/2 cosine of 60.
Yeah.
So that gets us the z component of alpha 2. Um,
Gotta be
maybe
some
the x and
symmetry.
y could be determined by looking at theta 2.
Yeah, so okay, so this is what am I thinking? This is square root 3 over 2, right? Some new variable. I'm parameterizing
Oh, okay.
all possible solutions.
Because the magnitude has to
Yeah,
be 1.
I was gonna say you could let one be 0, but okay. So where's beta on our picture?
Um, good question. It's gonna have something to do with whatever the alpha
So
3 is, I assume.
so that alpha 2 there, it'll have a 1/2 vertical component, and then the horizontal component is in like an arbitrary direction in the XY plane, right? And that's where beta, that's what beta is telling us.
Yes.
Okay.
Yeah.
I think
So
I get
what
it.
beta does, I understand, but I don't see how to draw it in a diagram.
Yeah, I'm not good at
Yeah.
drawing 3D. God help me with the 4D.
You just you draw 4 axes and you just assert
We,
that they're perpendicular. You just say it, and you
oh,
say it confidently, and the more confidently you say it, the more true it is.
okay.
The confidence correctness correlation. Um, if we did the same exercise for theta 2, what would be different? Would we switch just the sign? Like if we dotted alpha 1 and alpha 3, I guess. Are we just switching the sine theta and cosine theta? I think the same thing should be true over there.
Ooh, yeah. Yeah, so with a different beta.
Or a different beta. Okay, yeah.
Oh, yeah, no. So that's exactly it. And then you dot alpha 2 and alpha 3. And the assertion that that's 120 degrees solves for beta. Or if I've done something horribly wrong, then there's no solution. But usually this turns out miraculously.
So wait,
So wait a second.
is it
So
switching
Don,
sine and
weren't you said X and Y can be flipped for alpha 3? Is that what you just said?
I was just kind of
Just
guessing
reverse the
that.
sine and cosine? Hmm.
That's complete intuition. I don't have any justification for it. Um, hey Thunder, it has been a long time. I hope you've been good.
It feels right, because if one of our unit vectors is just z, then the other two by symmetry should have the same z component, right? That feels right.
We just did it. Can we get an answer that makes sense? I think that's the test. Maybe there's like you could do pi over 2 minus beta for each of those, and that's a better justification. Or somewhere it's some argument like that. But if we dot alpha 2 and alpha 3, Thunder's asking, is this special relativity but 3D? I assume asking about general relativity. I think this was probably better answering that than I am, but we're super early on, so we're starting to looking at different types of geometries, like on curved surfaces. But I think the bigger part of your question is special relativity. I think deals with simpler cases where things are constant velocity, and general relativity has accelerating and rotating things. Is that right, Fizzbuzz?
Yeah, I would say, but I would say this is like a poor man's spherical geometry, spherical trig stuff.
Okay.
Yeah, this feels like what we're
This
doing right
particular
now. Just
exercise.
yeah, this feels like a Calc 3 question almost. Like I wish I had you know what I wish I had was an orange and a Sharpie marker. That's what I want right now. I feel like yeah.
Yeah, I did hesitate on answering because of exactly what Dr. Cook is saying in chat, that special relativity can deal with
Oh,
accelerating
really?
frames.
Okay.
Yeah, but you need like calculus stuff, so it's still kind of closer to GR.
Oh, we have a similar. We want pi minus theta too. Space time is curved. You need general. Okay, thank you, Cook. Well, why do I have two variables now? Maybe I am doing something wrong.
Is
Wait, no,
theta 2
we know it's
also
120. Yeah, yeah.
Okay.
Or yeah, so we just get 60. And that's 1/2. Okay, and then in theory we can solve this for beta. So that's 3/2. Wait, I guess 3/4 sine 2 beta if I use that half angle. Am I doing that too quick?
Okay.
I think that's right. It's equal to 1/4. Oh, we're gonna get a stupid non-unit circle thing, aren't we?
That's okay.
1/3. Oops. Scaldraw is complaining, but I guess we're getting towards the end of time anyway. Half arcsine of 1/3. I guess, yeah, we don't care necessarily what beta actually is. We just care that it gives us the values that we want. Hey, Central. Do anything about Ultraviolet Catastrophe? I have never heard of that. I'm sorry. And I'm not sure if I'm pronouncing this right, but Nawang? This is a reading group on general relativity where I get a Discord call with people who want to discuss general relativity, and we solve some problems together. So we're working on... We've gone off on a tangent, but we're trying to draw a circle on a sphere with angles, all the angles at 120 degrees.
We can, if you want to abandon the question, we can. It can just be something we play with later. If we're
I think
slowing this down too much.
This might be something that I like verify that we get the right dot products, because I think we just found the beta, and that's we theoretically have the answer if I didn't make a mistake.
Yeah, and then the I would say the existence of these vectors that satisfy the formulas that we have proves that we can have 3 great circle arcs. Their intersection is all 120 degrees, like any pairwise intersection.
Right.
So it must be the triangle that we're searching for. And that's the hard way, right? I think the 90, 90, 180 is goofy, but it's kind of okay.
Yeah.
This is a much prettier triangle.
And so you're not a fan of the 179-91 thing because we haven't proved that exists, right?
Yeah.
Okay.
Yeah, we haven't proved that the belt loop, is a great circle.
Okay.
Great arc.
The answers are in the back of the book, but we kind of made up our own question as the issue, so the author didn't predict our curiosity, I guess.
Well, I'm gonna hop off. I'm definitely gonna make a figure for this and post it in Discord.
Oh, yeah,
cool.
thank you.
I'll post that in the reading group.
Okay. Thanks so much
All right,
for
see you.
coming by.
Thank you for organizing this. Having a
Yeah.
Yeah,
blast.
see ya.
See you, Buzz.
Dot products and circles and okay, bye.
Good stuff.
There's still a few minutes left for the 2-hour mark, Fembox. Like, we could at least think about C if you want, or if you want to dip out 2, it's okay.
Actually, I had thought about C because I read some of the questions earlier in the week, and I'd thought about C a little bit, but I don't think I have an answer to it. Had you thought about it at all?
I haven't even read it yet, to be honest. Maximum sum of
We're
angles.
kind of using that same formula and trying to maximize the angles inside the triangle.
Uh, I mean, I wonder if I'm limiting myself, but I keep going back to like, oh well, you have to take the short. Do you have to take the shortest distance? I guess you probably
That was my question too. That was my question when I was thinking about it, because
using that equator thing. Just take 2 points very close together, but go the other way around.
yeah, the thing about I don't know, thing about a triangle, right, in the plane is you sort of you know if you're inside or outside the triangle, but when you're on a sphere, especially when you start making these angles big, I feel like it's kind of you kind of lose a sense of which part of the sphere is inside your triangle and which part is outside.
Yeah, I guess I guess the question is if we're allowing 181-degree angles, like, or that seems to be like the breaking point. And
If all of them could get significantly close to 180, what would we get? We'd get 3 pi? 3 pi, right?
yeah,
Without pushing any of them past 180 degrees, we could get 3 pi. But if you look at equation 2.4, though, what's the surface area of a sphere? 4 pi r squared, right?
oh, I didn't even look at the formula. Yeah,
So if we could kind of push a triangle to cover the whole sphere somehow, we could get it up to 5 pi. But I don't think that's fair, because then you're kind of like you said, all your angles are way bigger than 180, and that doesn't seem fair.
yeah. And so Shane, that's kind of the idea that we're talking about. Like, if that's legal to do on a sphere, I guess. um, according to 2.4, for a spherical triangle of area A, if we made, I mean, what if we just like, I'm not even trying to visualize it, but if we just set A equal to something like, if we make A approach the surface area of the sphere and like what pops out? Um, it's 4 pi A squared, the surface area of a sphere, I think.
Yeah. Yep.
Okay. Oh, that's where you get the 5 pi from.
Yeah, that's where I was getting that 5 pi. Yeah, like Shane said, you could get a tiny little triangle, right? Just at the North Pole or something, just a tiny little triangle, 1 meter on a side, and then say, oh, I'm going to define my triangle to be the outside of this.
It's a really messed up triangle, but we haven't been given a rule like that.
Yeah, I don't know if they said that the triangles have to have. What's the?
I feel like this
Obviously,
is
the rule
maybe what
for
they're
you.
going for.
I guess the rule for Euclidean triangles is that no angle can be like 180 or bigger, right? Oops, did I just leave the Discord?
No, you're here.
Still here?
Yeah. Like, I mean,
I clicked the button to get rid. Oh, here I am. Okay.
yeah, if we did just think about Euclidean geometry, if we just took an acute angle, like we're allowed to measure it from the, like we do this all the time in the unit circle, I guess. Measure things that are greater than 180 degrees. I'm warming up to this. I feel like it's weird, but we can do it.
Yeah, I think the answer they're shooting for is either 5 pi or 3 pi. I'm going to lean towards 3 pi.
Where's the 3 pi coming from? Oh, just by limiting it?
Just kind of make each angle get as close to 180 as possible without actually touching 180.
Okay.
Is there a way we could get that on a sphere? I wonder.
I would assume we could follow some argument that we're doing for the 120 degree, like make them all 179 or something. Be
Yeah.
a lot less clean. I feel smart I feel right now that you are all discussing that seriously. It's kind of a cool thing. Like it's hard to visualize, but like you can. The triangle always out of 180. Unfortunately, that's not always true, Thunder. That's what we're dealing with. Are you okay if I check the answer in the back of the book or in the solution key?
Oh, for number 4?
Yeah.
Yeah, if you want to.
Okay. Doo, doo, doo. Okay.
Oh, it's a 374-page solution manual. God, that's long.
Oh yeah, it is.
Where'd you? Is that on the Discord? You said?
Yeah, it's in that. I can maybe find the link. I don't remember where I downloaded it from originally. It's in the Google Drive link that I uploaded. I could try searching
Yeah.
again for the answer keys. I don't remember what website I got it from. Oh, and I'm sorry, Nawang, I missed your question. Tensor products, I think those do come eventually. I'm only learning this for the first time though, so I don't know exactly what is coming. We're going through in that third dimension. Yeah. Good run rule, I thought. Oh yeah, Hunterfix. That's called some big YouTuber made a video about it, like Veritasium or through Blue and Brown or something. But it's Euclid's fifth postulate, which is that there's like 40 something equivalent statements, but one of them is that the angles in a triangle add to 180 degrees, and if you allow yourself to break that postulate, that's where you get non-Euclidean geometry. Wait, no. And the answer for 4, they let that top angle equal 180 degrees. We thought about this maybe harder than they intended. We're doing the equator with 2 right angles thing. It's the boring way, yeah.
Hey, they did go to 5 pi. Come on.
Yeah. So I guess they do allow the complement of a small equilateral triangle. Yeah. So it's the exact thing that Shane was saying.
So that counts as a triangle? Okay.
Evidently, yeah. Wait, the 3 interior angles are each 2 pi minus pi over 3. Oh, okay. Yeah, it's this statement here where they say it's the complement of small equilateral triangle. That's basically the thing that you said. Go buy a lottery ticket. Pythagoras and shambles.
That's a good question.
Yeah. Okay. I guess maybe we'll wrap up the reading group for the day there. This is exciting.
Yeah, sounds good.
So we'll meet one more time on chapter 2, and then the Saturday after next we'll do chapter 3, and that's only like 11 pages of reading. So I don't think it's going to be as bad as like Purcell's book, like 40-page chapters. Actually, I don't know if they are all that short. Well, that one's like 20 something. Okay, they get into the 20s, but not like 40. Okay, but yeah. Thanks for being here, Hembox.
Yeah. Thanks for setting it up. It's a lot of fun.
Yeah. So I'll talk to you later.
See you next week.
Yep.
All right, bye.
Bye. Okay. We are going to switch into a normal math help stream, but it was so much fun to do this reading group on electricity and magnetism last year, and I'm really excited to see where this one goes. So we are going to switch into just doing like a math stream here. Let me change over some like title and category and get some music going and stuff though. I should probably get music going. That's the first playlist I see. Let me get that image that we made today for the Excalidraw. Chapter 1 and 2, Part 1. Okay, so I need to change Twitch title and category and YouTube title and thumbnail. Yeah, this is like literally the very first meeting we've had on general relativity. So this is the easiest time to be engaged for those who want to think about it. From chat and studying. Math. Okay, Twitch is taken care of. Let me take care of YouTube. I kept on saying last time that I should just get a hotkey to do this, and I never did it that time, and I probably won't do it this time, but I'll keep saying that I should. Because I think I could accomplish this just with a hotkey. I'm doing the same thing each time. So I missed one stream for you and YouTube, so I probably doing. Okay, so I guess we've done 2 of those, and Zach says he has an idea for another one that will be. Oh, it's to the top. Oh yeah, thank you so much. The double prime. Holy crap! Thunder and Central, thank you both for the primes. That's a hype train right there. We planned that? Sawyer's not used to wearing headphones. That's fair. I hate the headphones that like stay on top of your ear. That type is the worst. 6 months of rehearsals? Yeah. You guys nailed it. Thank you both. Okay, I think I'm all updated. Let's go back there. Oh yeah, so what I was saying before, Thunder, is that so yeah, we've done 2 programming competition streams. And hopefully at some point we'll do a third, at least one more. And Zach said he had an idea for something that isn't like speed coding, something that'd be a bit like maybe more of like a project or something that would take more time. I'm not sure exactly what he has in mind, but there probably will be another one. Or do they always had Amazon Prime, never signed up for Twitch until this second? Or you never like connected it with your Twitch? Oh my god, Central. I can't believe it. You're a washed up streamer, but you know you have streamed, and you don't like use your Prime sub. Unbelievable. But yeah, we don't have it's just like a concept for now, Thunder, but it is something that we've like talked about. Do I want to do the maybe okay? If someone has a math question, please do let me know. But in the absence of a math question, I might do that thing that I said that I would do for once in my life and verify. Jose Marcos? Oh yeah, hit me with it. You can type it there in chat, or you can put it in my Discord. Whatever's easier. Why is this crappy? Zoom and enhance. Let me... Is that better? That's better. As you help me understand the ultraviolet capacity or catastrophe capacity. Sure. Catastrophe. Apparently, I've seen this before. It happens to me so much where I Google random things on stream and forget about them the next second, and then someone else asks about them, and I see the purple link. Okay, Jose, I see your question. Let me think about what Thunder asked just for a little bit, and if it seems too complicated, I'll pause Thunder's question and go to yours. If you have something that emits radiation of all frequencies and you have a perfect absorber or black body, you should have an infinite range of ultraviolet waves? Oh god. You don't get Planck's theory on it. Okay, this is a little too much for me. Let me Jose's question I actually know how to do, and it shouldn't be too long. Well, let me do Jose's first. Oops. I was very enjoyable there. Sometimes try to explain with total graphs, just mathematical intuition. I probably name it. Okay, Merc. Yeah, if you find anything that would help explain it, please feel free to let me know. Okay, so 2x squared minus 2x over x squared minus 3x plus 4. We want to plug in natural numbers of x such that this entire thing comes out to also be a natural number. And to try and make this like into a simpler case, like the way that we guarantee that is that the number on top should be divisible by the number on the bottom. So if we had like 4 over 2, we're plugging a natural number into the top and bottom, but it'll reduce to just a natural number 2. So I think it'll be helpful to factor these two things because we need to think about factors, and that's what factoring is. So from top, I'll factor out a 2x. We'll get x minus 1. From the bottom, we get x minus... Wait, am I dumb? That doesn't factor, does it? Is there a typo in the problem? Should one of these be a minus? Joshy. Oh, are you Jose? Oh, okay. There. Oh, okay. So okay, I'll call you Jose then. um. I feel like I'm making a dumb mistake. I feel like this should factor, but maybe it's not supposed to. Division? That's something to consider. 9 minus 36. Okay, yeah, so it's not supposed to factor. Okay. My strategy that I was thinking doesn't work then, does it? It would factor if it was negative 4. Yeah. So we need to assure ourselves, I guess, that 2x is equal to some constant times the denominator. Don't know why I was making it into a z. Or that x minus 1 is equal to some other constant times the denominator. I don't know if that's a helpful thing to think about, though. There shouldn't be that many solutions here, right? I thought this would be a simpler one, to be honest. um, I mean, we can see that x equals 1. It's going to give us 0 on top. And so we're just going to end up... Oh, are we dividing by 0, though? No, we're not. So x equals 1 will definitely work. But, you know, we probably shouldn't guess and check for all these. Does 0 count as a natural number? Because I guess 0 would work too. I think in the math context it normally doesn't. It might vary by country though. Um, okay, what does long division give us? Maybe Thunder is making the right call. Doesn't seem useful. Hmm. Let me just see it for myself, I guess. I mean, it gives us a bit of a smaller problem at least. Yeah, so really just have to boil it down to this problem. And we only need to look for solutions where x minus 2 is greater. No. Not necessarily greater than. Because the 4 might save it. Okay, so let me not factor the 4 out. We only need to look for solutions where this line is greater than the parabola. Because, like, if we grab a line and a parabola, I don't really have this one. The parabola is something like that. The line will be something like that. But the parabola will always outcompete the line in the long run. We only have to be concerned with that section where the line is greater. So maybe we can find the intersection points and just plug and chug between the intersection points. Because if 4x minus 8 is less than the bottom, I think we're just screwed unless the bottom equals 1. I think Mert has the same idea, it looks like. Yeah. So we want to... we have potential solutions. Yeah, folks, that was my original idea, but I don't know... Or I guess that's a combination of these two ideas, but I don't know where you go with it. We can have check for solutions. Yeah, that's what I want to do, Thunder. Check for solutions when denominator is 1 or 4x minus 8 is greater than or equal to denominator. Those are the two areas we need to be concerned about for solutions, right? So 4x minus 8 greater than or equal to x squared minus 3x plus 4, and now solve this. X squared minus 7x plus 12 less than or equal to 0. Please tell me this factors. Oh, it does. Thank God. Less than or equal to 0, and now we can use a sign chart. X should be between 3 and 4. Yeah. So that is great because x has to be a natural number. So we only need to check 3 and 4. Oh, that has to be a perfect square. Interesting, Fembox. Um... 0 and 2 are also solutions. 0 may or may not be a natural number. That depends. Some people start natural numbers from 1, some people start from 0. We can include 0 for completion, though, because it definitely works. And 0 and 1 I'm getting from guessing and checking. 2... We probably just guess and check it, but... if x equals 3, we get 12 minus 8 for 9 minus 9 plus 4. That's looking good. 4 over 4 is 1. X equals 3 works. Yeah, as long as we don't get 0 in the denominator, we're good. And actually, we know we don't. Yeah, so x equals 2 works. We should make that another OR. Then x equals 4, we just check that. 16 minus 8 over 16 minus 12 plus 4. Eight over 8? Keep getting 1s. That's funny. Okay. So yeah, I think the answer is 0, 1, 2, 3, 4, Jose. And it can't possibly be anything more than that. And unfortunately, it seems like the only way you can solve this is by looking at cases and making sure you've covered every single case. So there's cases where the numerator equals 0. in the original problem, and then if you do this division, you have like the problem. You have to like repeat the problem again. As far as I know, Jose, yeah, it's you can't just do enough algebra to solve it. You have to do some thinking too, unfortunately. And so thankfully the numbers are all pretty small. But yeah. So I don't know, if you have any questions, let me know. If not, I'm gonna go to trying to figure out the ultraviolet catastrophe. Good luck. Yeah. So let me try to understand what the problem is. Okay, B sub lambda is the spectral radiance at that wavelength. And lambda can theoretically be anything greater than 0, I assume. The power emitted per... Okay, yeah. C is speed of light, KB is the Boltzmann... Okay, sure. T is temperature in kelvins. For frequency, that's probably... Oh, what? New? I think that's that... The Greek letter looks like a V. Okay, yeah, sure. That doesn't matter, though. The expression of the fact that the formula misbehaves at higher frequencies. As the frequency goes to infinity, so does the power emitted. Okay, sure. It's. I think you should start by understanding what classical wave theory suggests and makes it a lot easier to understand. Is that what I'm doing here, Thunder? So I think I at least have a 15% understanding of this now, or I might understand enough to move on to what the solution is. Well, no, I think Planck's theory is down here. Rayleigh-Jean's law was the classic physical approach that to that problem. It failed at short wavelengths, and on top there was a good graph for that. Okay. Okay, so this stuff right here is what was causing the problem as I'm reading it. Because as frequency goes to infinity, it predicts infinite energy output. Looking at this expression here. Or only as wavelength goes to 0 in this one. B, the power emitted goes to infinity. Mert was saying that this graph is good. Interesting. So I think what the caption is saying is that the black line is the ultraviolet catastrophe one, where it shoots off to infinity the shorter the wavelength is. And that's the same thing as frequency being big. And so the corrected versions, I think, are these other colors. So I guess the Rayleigh law was only good for pretty big wavelengths, it seems. So yeah, it's supposed to come back down and behave better, but the Rayleigh Jeans law doesn't. Is there a Billie Jeans law? Oops. What a figure the triangle found. Ooh, nice. I'll take a look at it. Actually, let me just look at it quickly now. What? Fizzbuzz, you mad visualizer. So like the 120-degree triangle is like right in there. Vertices 0 and 0, 2 root 2 over 3 minus the third. I think that's about what we were getting with the beta. We're getting more. Oh, okay, you have it oriented a little bit differently, maybe. Since point was chosen as 0, 1, 0, and we chose 0, 0, 1 in our scratch work. Levi Jeans law, they don't last as long as they used to. That's awesome, though. Okay, yeah, it took me a minute to figure out what you were saying when you very first said the planes intersecting with a sphere thing, and this is a nice way of like showing it. Nice. Thank you for doing that. Max Planck quantizes the propagation and infers that such an increase at each wavelength can be propagated in a certain way at certain wavelengths. Also, there is lines displacement law for peak points for it. Okay. Is there a reason why it doesn't go to infinity? So I assume, Thunder, your most recent question is about why Planck's thing does not go to infinity here? So they pack soccer balls when shipping? Oh, they probably, yeah, they... that is how it looks, isn't it, Orange Hue? Let's find out. So first off, he quantizes stuff, which is what Planck is known for, right? Rather than thinking of things as a continuous like wave. By applying this new energy to the partition function in statistical mechanics, Planck's assumption led to the correct form of the spectral distribution functions. So this is the updated version of the flawed Rayleigh genes. And so this is wavelength. So we're thinking of this as the wavelength goes to 0, as lambda goes to 0. What happens in this limit here? This piece that's being multiplied is still 0, or is still going to infinity. This piece here, though, is 1 over e to a very large number. So oh, I see what's happening. Yeah, let me... Yeah. Oh, Okay, well, before I do what I was about to do, how does electromagnetic radiation being in discrete packets lead to low intensity for high frequencies? Well, it seems like the energy of each individual packet. Oh, well, that's increasing as lambda gets small, isn't it? Um, that I think is too physicsy for me to feel confident in explaining. Um, I'm thinking of it as like I'm just kind of generally thinking of how really short or like high frequency radiation is the dangerous type, right? Like gamma and alpha radiation, it has a lot more. I guess maybe it's more dangerous because it has more energy. The shorter it is, but that's kind of my guess. Like I don't know why. Um, yeah, the E equals HF thing. That's experience background is important there for understanding it clearly. Okay. Yeah, Orange, you. Thunder's question is about just trying to understand the ultraviolet catastrophe and why it's not real. Um, but yeah, so Thunder's question is about why does the the quantization of this energy imply the high frequency has more energy? Like, why does quantization do that for us? If it does, that's where my physics is failing me. Hey, Lucas. So something with how much energy is scattered over an area. Yeah, I think that's what this B thing is measuring. It's just shit math. It's physics, so depending on how there's a lot of people who call physics shit math. Yeah. Uh, I think it's because on the black body, the energy density must reach some minimum quanta to emit energy. Maybe, yeah. I think they're saying something like that up here. There could be no fraction of a discrete energy package. Can't even see the difference. It was along the lines of this, but went out my head fast and went in. I'd never taken a class in this stuff. I remember in my electricity medicine class, we did get to derive E equals mc squared, but he kind of skipped over all the background of it. Yeah, Lucas, the speed of light squared. I think in some way this formula leads to E equals mc squared, or like there's some relationship between that and it. Um, you're not going faster than c. Um, the energy, it's just a formula. energy just happens to follow mass times the speed of light squared, but it's not, nothing's going faster than c. Finite amount of energy is distributed evenly among the quanta. Quantization takes crucial role for photoelectric effect. Maybe more understandable quantization of light from a different perspective. Okay. What I'm getting is there. I mean, I don't know. Quantization solve this. Basically, it says you can't radiate less than a quantum of radiation in a particular wavelength. According to Planck's quantization formula, equals hg over lambda. Very short wavelength has a very large quantum. It will be radiation predicted by the black body formula as large, but not as large as the single quantum. Ooh. Thank you for finding that. Links are turned on as well if you want to drop the link to the thread. It won't get nuked. Okay. This seems like this seems like Thunder's exact question here. Black body would radiate energy not just around a given average wavelength, but also in all wavelengths. You can't radiate less than a quantum of radiation in a particular wavelength according to Planck's quantization formula. A very short wavelength has a very large quantum. So if the would-be radiation predicted by the blackbody formula is large, but not as large, so no radiation be emitted in this wavelength by the given process. Interesting. I think, Thunder, it's kind of like what you were saying before, where the Rayleigh-Jeans formula assumes that all the atoms spend all their energy, but it sounds like the quantization piece means they can't spend their energy until they hit a minimum threshold. And so only a small minority of the atoms actually end up spending this energy, and that's why it curves back down, because most of them just can't spend it. That's how I'm thinking about this. That's my kind of barely educated guess. Is there a formula for a black hole? It depends what you're trying to measure about a black hole. Like I've learned about something called the Schwarzschild radius, which is the radius of the event horizon, like where it turns actually pitch black. it's not a complicated formula. It only works in certain conditions, but there's many formulas about black holes that I'm not aware of too. Quanta would be the specific set energy amount of a photon if photon has, if I remember correctly, a little packet of energy, so to speak. Yeah. Energy would depend on its frequency. Planck suffered albinoism. Never got to truly experience sunlight. Really? I never knew that. So Thunder, you said earlier that energy, there's a finite amount of energy and it's distributed normally among the quanta. I can't confirm or deny how it's distributed. But I think what it's saying is that all the atoms or molecules have a certain amount of energy, but only those with that, like, there's a cutoff point before they can radiate it. And only the ones above that cutoff point actually radiate anything. So rather than every atom spending all the energy it has, only the ones above that certain energy do. That's what it seems like to me. So the only other point I was going to make was that what I can be more confident of, if like the reason this thing behaves better is that you could literally take the limit as lambda goes to 0 of that formula. Let me just bring it up here because I don't want to rewrite everything. Like this piece would go to 0 like a quintic. But this piece, I think, would go to infinity. Wait, is it? Lambda is very small. It's e to a very large number. No, it's going to 0 also, I think. E to a large number is a large number. A large number minus 1 is still a large number. So yeah, these are both going to 0 now. Oh, I'm sorry. I had the first part backwards. That's why this didn't make sense. The green piece goes to infinity because we're dividing by 0. And that was the issue. Like, this green piece going to infinity is why this thing was broken. But multiplying by this factor that goes to 0 makes it behave, because the exponential is much stronger, or the exponential going to 0 is much stronger than a quintic going to infinity. And so that's why it, instead of shooting up, it comes back down. That's mathematically why that correction happens, at least. I don't know if that probably wasn't a part of your question, but that's the only kind of smart thing I can say about this. We just sound explains exactly like what I remember reading. Okay. Kind of like the activation of every chemical reaction, but also not. Yeah, it's something like threshold that happens, I think. Maybe a stupid question. What's the difference between quantum, photons, quanta, and corpuscles? I never heard of a corpuscle, to be honest. It sounds like a part of the body or something. Oh, Ohms. Thank you for the follow, dude. 2 + 2, 3. Welcome in, dude. 5. Yeah. Only good math here. 6. Atoms basically need Planck's permission before sending off on the photon they're lovingly grown and nurtured for the microsecond since birth. What else has to be right, statistically speaking? Yeah. Just name every number. Quantum photons corpuscles. I'm probably not saying it right. Is it corpuscle? Corpuscular theory of light. What the hell? Oh my god, the power tower, Lucas? I don't know. I don't want to do that. Newton was dumb when it came to light. Frickin' Newton, man. What a nerd. Light, quantum versus corpuscles. I want stack exchange, to be honest. Corpuscle? Okay. It seems like the corpuscle thing is older and probably not as right. Okay, physics stack exchange. These seem pretty similar to me. Opposed to wave theory. I guess the corpuscle thing doesn't capture the whole wave part of this, I guess. These travel in straight lines is maybe the key difference. And not in a wave. Is the issue. That's what it seems like. This is another example of you doing problems I have some understanding of, but you're way more advanced. I've never studied this stuff before. I'm just spitballing. That's equations for modeling light. Okay. Photons are a subset of corpuscular theories. The more general theory doesn't tie corpuscle energy to frequency. Huh. I would trust Ivan on this over me, easily. So. Difference between quanta and quantum. I think it's the same word, just one's an adjective and one's a noun. A quanta is the actual packet, and you have a quantum something. Oh, or it's the plural? Okay. Pre-quantum mechanics theory. I would think so, yeah. I wouldn't know. Quanta is the little brother of quantum. Is a photon a bunch of quanta? I think a photon is one quantum. Question mark. I don't know. Okay, I got that right. Photons was used for a camera. I mean, a bunch. Yeah, it captures them. I'll put the link to this in chat. I think you're fine with it. Yeah, thanks for the question, Thunder, and thanks everyone who hopped in to save me there. Lucas, a good website for self-studying math. I mean, I'm a shill for Paul's on my notes. What type of math are you trying to study? Like, just calculus? If so, I'd say this. Discussion doesn't rely on math. What is fun? Ooh. That's a much tougher question. See, the unfortunate thing is that once you go beyond calculus, I don't know of all-in-one websites like OpenStax or Paul's Online Notes that try to wrap up a bunch of stuff into one thing. Honestly, I would probably look at 3 Blue 1 Brown videos to see what areas of math exist. And if one just really like strikes your fancy, me or I can find someone who can recommend you a textbook. That's usually, or you can find a lecture series on YouTube. I could find one too. What's your angle on this? 3 Blue 1 Brown. Very big YouTuber. He makes pretty amazing math videos. And so, like, this one here is one that like came to mind for me. Like, if you want to know what topology even is or what type of problem it deals with, that's a cool video. He has oh yeah, if you don't like shape math, stay away from topology. He has like a tour through differential equations or something like that. Does he have a playlist for it? Essence of linear algebra. But honestly, yeah, like the only type of math you like is solving equations. That's a lot of math. Like, a good stepping out point for you might be some of his like differential equation stuff, just to get a feel for like what it does. And if you want to learn more about it, then like we can try and guide you from there. But you kind of have to figure out what sub area of math you want to learn about. Yeah, his videos on PDs are really good. Dexter Chua and David Bai have a bunch of sets of lecture notes from course at Cambridge, but they're very dense. Okay. Also, hey, Emma. Where geometries and angles, we just call it a rounding error. Okay. Oh, that's funny that you linked that, Mert. I've been meaning to watch his videos because he streams on Twitch also. Him making the videos, but this is another channel that Mert in the YouTube chat is suggesting if you want to just learn about different areas of math. I can't vouch for it myself, but they seem like pretty well made videos. What base knowledge? Oh, for 3-1 Brown in general, just watch the video. Don't worry about base knowledge. Even if you can't follow everything about it, he's really good at conveying the ideas. Oh, was there? Was that why South Korea is over? Is that why Lucas said that? That's not here anymore. Well, I think South Korea is doing fine. It's not here anymore now. But yeah, I don't normally watch YouTube through this account. I just kind of sub to a bunch of people who I like to support them, but I don't usually watch videos through here. Going to sleep now? Alright, sleep well, Thunder. So, hey, Matthew. Oh, hey, there's a South Korea's over. Oh, it's Kurzgestat. I never watched a video of his, but I've heard of him. I don't know how you pronounce it either. Spend some time on YouTube, catching up some of these math videos. Yeah. I don't watch a lot of math on YouTube. I always have a hard time, like, just seeing the runtime on videos and wanting to commit to it. And it's terrible because I'm like, oh, I don't want to watch a movie because it's 2 hours long. And then I spend the next 2 hours not doing anything important. Anyway, so it's like I should just have watched the movie. Oh, this one? It looks really emotional. Like, this one is, I've seen it recommended to me before, and it's kind of like, it does a good job of, like, grabbing me. So I was looking for shorter. Yeah, exactly, Ivan. It's bad. I have a lot of tabs open. Okay. If someone has a, I guess we're at a little break point here. If someone has a question, let me know. If not, I'm gonna pull something to study, I guess. All math explained in X minutes videos? No, I haven't. Let me pull out a textbook. We'll probably do linear algebra because we just did the physics reading group. What is algebra really? The more I learn about math, the less I know what algebra is. If you see, if you're at university and you see a course called something algebra, the lesson I learned is to be scared of it. Ugh. Amitablam is giving you the real answer, which is it's a very general word for how humans think of I guess, yeah, like objects and how we can combine them. And if that sounds vague, it's because it's supposed to be vague. Yeah, exactly. Because linear algebra is the study of types of math that has certain properties that we call linear. There's many other different types of algebras that have other properties that people study too. There's abstract algebra, which is you never talk about a particular type of object or a particular operation between them, but you try to generalize for all of them at once. It's very abstract. Which is I meant that in general. I didn't just mean to say abstract algebra is very abstract. But if something exists, that means it therefore must exist. You basically build up from obvious statements like that into more complex and meaningful statements. So that a statement like that is where you might start in an abstract algebra course. That's called reflexivity. That's basically the idea of it. Sets, groups, rings, fields, vector fields, CK manifolds, those things called categories. What algebra special? So yeah, you can take algebra and abstract up another level, and I think you need to abstract another level above that. It's you're talking about everything and nothing at the same time. a lot of math for physics, but can never understand pure math because I had no idea what the goal was. It's like I could only understand math ideas that had a physical analog. I have the same struggle, Ivan. So I have a bachelor's in applied math, and I'm planning on starting a master's in applied math in the fall. And from what I've heard from people who like pure math, they just abstract for the sake of abstraction. That's what they like about it. They want to make the most general statement they can. It's like a competition in that way. 0 exists minus x and x are in between it, unless 0 equals x. Yeah. Stuki, I can't find the post I made on the topic, but being a math major is just get a B in algebra 1, get a B in algebra 2, get a B in algebra 1, get a B in algebra 2. Yeah, it's all just different sorts of algebra classes. You think you're only good at calculus, seeing what's I kind of like? I mean, just try to like get yourself exposed to all sorts of types of math. You might surprise yourself. You might also not surprise yourself, because I feel similar. Like, I love calculus and things that fall directly from calculus. I can't say the same for like a lot of types of pure math. Which there is, like, you know, calculus and pure math, but I like to apply it. To get past that stage, get stuff like algebraic topology, algebraic geometry, yeah. Algebra analysis, probably in statistics. There you go. If I don't type anything, there isn't anything that I typed. Yeah? You're basically doing tautologies. Hey, Rapture. Oh, Rapture. You missed out on the reading group. It was a couple hours ago now, or I guess it ended an hour ago. But there'll be more. Yeah. Eugenia Chen's Joy of Abstraction. Let me see what that's about. Joy of Abstraction, Eugenia Chen. Switch to math, category theory, and life. Wow. If you can make category theory interesting, you are a very talented person. At least interesting to me. There's a lot of people who are interested in it. But that's kind of an interesting premise for a book. That's kind of neat. This has me interested to read at some point too. How big is calculus really all of math? How big is calculus really of all of math? Bobos, hey, how's your Saturday going? How, like, it depends how big you make it, I guess, but I would tend to agree with Amma de Blam that calculus doesn't have a... If you consider all of math, it doesn't occupy a very big part of it. It is the jumping off point, I think of. It doesn't have to be. In the normal progression of education, it is normally the jumping off point. But you could spend your entire life learning math and never learn calculus. I guess that's what people did all throughout history before Newton. Unless you're Archimedes. Beat Saber with a friend? Oh, I played that once, and it was a lot of fun. It was also a workout, though. Application abstract algebra cryptography is one of them. Oh, I didn't know that. Sometimes their ideas become very understandable, freezing fields and rings, creating encryption and decryption. That's neat to know, Mert. But Lucas, you if you wanted to, you could spend an entire lifetime studying things that just follow from calculus. Like, that's why I was kind of saying that you should look at differential equations, because there's something called partial differential equations, which are a very active area of research. And they're also just pretty dang cool. Analysis and calculus are very similar. Analysis is calculus with proofs. In normally calculus class is just like the concepts without proofs. But yeah, it like you should try out everything in my mind, Lucas. But from what I've seen you say, like you probably like to stick to applied math, because you kind of get a baseline knowledge of calculus and you start applying it to other things. Like, I know I probably shown it to you before, and I keep showing it to people because I fucking love it. Let me find it. You don't really like applied math? But if you man, well, okay, if you don't like pure math, you don't like applied math. What math? I guess you just like calculus, but I mean that just keep exploring, I guess. But the reason why I like calculus is that it links things that are taught differently. And so this is the thing that I've shown a million times on stream. This is from physics. And using calculus, you can connect the electric field that is being generated by a bunch of charged particles with their voltage, with their charge density, and you can go all around in a circle from one to the other and figure all the others using calculus. And before you learn calculus, you just never really learn how things are connected like this. Like, you normally taught stuff like this. You don't be taught these three things pretty separately. And you don't have to apply math to physics. You can apply math to a bunch of things, but this is like, it's the type of stuff that just like makes me excited to like learn. Stuff you use in general life. You want to do calculus, but you want to stay theoretical. Well then, yeah, I think what Amadiblam is saying with analysis is probably where you want to lean towards then. I wish you sell material up from it, but like Zach or Eats Its White Pie has done now 2 semesters of an analysis class on Twitch. Lucas, you can absolutely get into analysis, and in fact, you're already doing things that are in a typical analysis class, like epsilon delta stuff. That's analysis. Anytime you're doing a proof about calculus, that's analysis. You know what? I already had a linear algebra problem up on my thing that I forgot about somewhere. It's this one, 26. I do kind of like it, but it's a bunch of bullshit. Fair enough. You're not wrong. You can build as tall of a tower as you want, but it's only as strong as the axioms that make up the foundation. You haven't heard me laugh like that ever. It's just, I don't know. It makes me. It just makes me laugh to hear that you like something, you want to study it, but also it's bullshit. Like, like, I feel like I don't really understand why you like math. If that's how you feel about it. I think I can see an angle. Like, it's a funny attitude to have. You understand why you like that? That's fair. If the physics works, I don't need your axioms. That's fair too, Ivan. You just take the math and bend it to your will. You have like an abusive relationship with math, it sounds like, Lucas. Ugh. No, but you like being in high school still, you're at a perfect like time in life where you don't have to make up your mind. You don't have to know the exact thing you like. Like, just follow wherever your gut leads you. You don't have to know why. Just kind of do it. You're specialized in general math where you know what you actually like. Then I can get into it. Yeah, I mean, to be honest, I'm having the same exact struggle when I was writing applications to grad school because they would ask you questions like, oh, what are your research interests? And the thing that's in the back of my mind is always like, how can I have a research interest before I've learned what's out there? Like, I feel like I need to take some of your classes and some of these advanced topics before I can really make an educated question to research. um, Force George to bring me. Oh yeah, Hamish, hit me with it. The incel excel Venn diagram meme. Wait. So incorrectly. Okay, I've experienced Excel incorrectly assuming something to date all the time. What does that have to do with incel slow? Do incels encounter that a lot? Two general math course, applied math, theoretical maths. You want to go to theoretical maths? Oh, that's fucking hilarious, Emma. They assume something is a date. I get it now. Oh my god. Oh, that's really clever. Indonesia out Indonesia. Did you get it instantly, Casey? Maybe I'm just slow. I posted it famished. Yeah, let's see. Oh, it was grayed out. That's a setting in the Twitch chat in the little like gear icon that's right next to the chat button. I'm just slow, I guess. I need to catch up on my incel jokes. Okay, so I assume the task here is just to simplify this and make it not look stupid. Incel, it's short for involuntary celibate, I want to say. It's not a good thing to be. It's the type of dude who blames women for them not being able to get a date, and there's all sorts of sexism and things like that wrapped up in it. Alpha male? They think they're alpha males, maybe. Or, I mean, I don't even know if they do. Cannot be used for life of me. I managed to compute one, but still. Yeah, there's a couple different ways. Oh, I didn't even know that, Casey. So, I like to start these by getting rid of negative exponents. Andrew Tate, I mean, incel is more like the fat nerd wearing a fedora than a buff alpha male. But they're both similarly sexist. Okay, so yeah, famous. I would start by getting rid of the negative exponents here because they just make everything worse. Negative exponents make life worse, usually. So I'm going to start by working inside the parentheses and focusing on that m to the negative 2. So a negative exponent means you can flip it down to the denominator and make it positive. So I'm going to do that. On top, we just have 3t cubed left over. On the bottom, we'll have 4m squared t to the 6 to the negative 3. Actually, women don't have rights. Yeah, like, they feel that women owe them attention. Negative bad, positive is good. Charge statements. Oh my God, Fizzbuzz. Okay, and so now we have this negative exponent to deal with. And so, in this situation, we can get rid of the negative exponent just by flipping this fraction. I could say more about how to justify that, but I'll just try to keep it simple. If you want to hear more about it, I'll say it, but if you have parentheses with a negative exponent on the outside, the end result is that you just flip the fraction here. So minus 9m to the 5th t, flip the fraction, cubed. So dumb parentheses. 0 equals 1? I guess so. Okay. Now things are looking a little bit cleaner because we don't have negative exponents. What I'm going to do next is I'm going to use a property of exponents, which is, this is all multiplication inside the parentheses here. And so when there's no addition or subtraction or anything weird like that happening. Oh, I confused you? Okay, yes. So actually there's more I could have done inside here. Now you pointed out, but this 4m squared t to the 6 went to the top. And then the top went to the bottom. Hey, Christian. Operational research math. Is it hard? I've heard of that as an area of research. I'd never studied it, though. To be honest, it probably has some cool math in there. I don't know. Is it hard is always, it's always relative. Both relative to other types of math and relative to you. So your famous, maybe I'll draw this out a little bit more because rather than just skipping to the end result. But yeah, Christian, I have a hard time saying like yes, it is hard or no, it's not hard. I would say it seems pretty interesting, but if you think it's interesting, you should probably just go for it, and or if you think you'll need it, like I don't think there's anything that someone can't learn. It's just a matter of time. So I'm not sure what the motivation is for trying to get into operational research math, but if you need to or want to do it, I think you should do it or figure out what you need to do it. Okay, so backing up, you're asking where I got the 3t cubed from. This 3t cubed here came from, it's what's left over here. I put the m to -2 down in the bottom because the exponent was -2. So all that was left over was the 3 in the t cubed. Seven steps in one step? Yeah, Lucas. I mean, there's always a balance to strike. And so, okay, so it sounds like you're on board with hopefully this step then. And so instead of doing the thing that I just did, which is maybe a little bit too much to do at once, like Lucas is saying, there's a couple things we can do here. I think I want to cancel, because we have a t cubed and a t to the 6 here. So 3 of the t's on top can cancel with 3 of the t's on the bottom, and that just leaves us with 3 t's on the bottom. Is your internet failing? That sucks. Harder than your grade after a functional analysis exam. Okay, so in this step, I just canceled t cubed and t to the 6, and I ended up with a t cubed on the bottom. I hope that's okay, famished. Unless I hear no, I'll progress a little bit further. That's okay? Okay. -9 m to the 5th t, just carrying that part over. Now I'm going to use a property of exponents, which is when you have a fraction here, I can put the -3 to the top and the -3 to the bottom. As if you want to call you father? Weird. You can do it though. I prefer daddy. Yeah, I much prefer daddy. -2 times -3. Oh yeah, you're right, Lucas. There's a lot of ways to do this. I'm just gonna stick with this way, but your way is valid too. Okay, so what I'm doing in this step, at least the way that I'm doing it is, I'm taking the -3, I'm attaching it to just the numerator and then just the denominator. That's a thing we're allowed to do with exponents. So we get 3 to the power of -3 on top. And then we get 4m squared t cubed to the -3 on the bottom. And now we have some more negative powers that we can get rid of. this 3 up here, since it has a negative power, goes to the bottom. And then this 4m squared t cubed goes to the top. Like wherever it is currently, it just gets flipped. So there's going to be a switcheroo that happens here. So now on top, we'll have 4m squared t cubed. So this negative 3 turned positive. And then a 3 to the positive 3. And so now we're in the glorious situation of having no negative exponents, and life gets a little bit easier. We still have a couple of steps to deal with, though. Well, 4 times -1 is -4, Lucas, but 4 to the -1 is 1/4. It's just different operations. You're gonna clip this? Okay. That's fine. Now what I'm gonna do is deal with these powers of 3. So this is all multiplication inside here. Oh yeah, that's awesome. This is all multiplication. So if it's all multiplication inside the parentheses, exponent rules say we're allowed to distribute this 3 to each of the things here. So it'll be 4 to the 3, m squared to the 3, t cubed to the 3. So let me write that out. 4 cubed, m squared cubed, t cubed cubed. You're going to bed? All right, sleep well, Lucas. Thanks for praying out. On the bottom here, 3 cubed, I'll just calculate. That's 27. Because it's 3 times 3 times 3. So that 3 times 3 is 9. And 9 times 3 is 27. All right, we're getting there. Now let's deal with all the cubes that are up top here. So 4 cubed is 4 times 4 times 4. I happen to know that's 64. M squared cubed. Hey, Vivon. When you have nothing much, how about you? In this situation where you have m to a power and then parentheses another power like that, the exponents multiply. So m squared cubed is m to the 6. Doing good? That's good to hear. Same here, we have t cubed cubed, so that'll be 3 times 3 is 9. Russian roulette earlier had a blast. Hey, Syntax. All of a sudden with AP Calc BC? Nice. That's huge. When is the AP test? Okay. May? Nice. Good luck. Yeah, it's soon. Hey, Color Cone. Okay, so now we have no more parentheses. We have nothing to simplify with exponents. I want to get all of the numbers in one place. I want to get all the n's in one place. I want to get all the t's in one place. This is all multiplication and division, so we can do it in whatever order we want. So I'm just going to switch around the order of these things. We still have a -9. We're still multiplying by 64. We're still dividing by 27. And then we have this m to the 5th, I'll place here. This m to the 6th, I'll put right next to it. And then we have this t here. And we have this t to the 9th here. Any tips for studying the exam you want to get a 5? Honestly, just do as many practice tests as you can stand. That's the best way. Okay. And I would be remiss if I didn't shill for Paul's online notes. If you want a resource outside of your class to study calculus from, this is a really good website. Just like look in the Calc 1 and Calc 2 sections, and they have a lot of really good practice problems here. So like if there's a particular area that you want to know more about, just like look in that section. Am to Blame is saying that the threshold for 5 isn't that high. You can make some mistakes and still get a 5, which is good to know. All right, so we're in the home stretch now. Famished. We have basically 3 separate problems to do. Like we have this problem, we have this problem, and we have this problem. Only a little bit more. So in working on this problem, I noticed that 9 and 27 have a common factor, so we can cancel it. So 9 goes into 27, so let's divide each thing by 9. 9 divided by 9 is 1, 27 divided by 9 is 3. 3 doesn't go into 64, so that's as simple as we can make that piece. So we have a minus 64 over 3 in front. When I used to grade at AP Calc exams, they had free response questions from previous year's exams posted on the AP website. Right, yeah. There's a lot of official practice tests, and there's a lot of unofficial ones too. Yes, I think there's unofficial ones. There should be. And now if you have m to the 6 times, or sorry, m to the 5th times m to the 6, since they have the same base, importantly, m, the exponents add here. So 5 plus 6 is 11. Same rule over here with the t's. They have the same base, so the exponents add. 1 plus 9 is 10. So they're, oh, nice. I'll pass that link along to Vivon in the YouTube chat. And so I'd say that's the final answer there. I think now we're done. So let me know if you have any questions on anything that I did there. It's a good stretch. Can close that. Sorry, I'm just doing some management of my windows. Oh, the BC ones? Oh yeah, that link was for the AB, wasn't it? No worries. Spam away. Okay, so I'm probably gonna wrap the stream up here. So Famish, if you have a question, just type something in chat to let me know, and I'll solve it for you. But otherwise, I think I'm gonna need to wrap things up. Yvonne says thanks, $10. Yeah, these questions are intentionally confusing. But it is really good to be able to simplify stuff like this, because you do get some crazy things you have to deal with in like a calculus class. So yeah, no worries at all, Famished. This is a really foundational skill, and it does pay to be good with this if you go farther in math. So I would recommend like taking your time with it and making sure you feel like you understand it. Okay, so as I said, I think I'm going to wrap things up here in that case. So YouTube stream is going to get cut off here, and on Twitch we'll look for a raid. So Vivon, anyone who's here on YouTube, thanks for being here. Tuesday stream is canceled. I should be doing games on Wednesday though. But yeah, thanks for being here, YouTube.